Hello there, and welcome to Just About Earth. I'm glad you're here. This is the place where we take big, sometimes unsettling ideas about our planet and handle them carefully, like you might handle something fragile you found in an old drawer. No rush, no loud surprises, and no pressure to keep up. If you're listening while you wind down, you're in the right spot. If you're listening while you do the dishes, that works too. Earth does not mind when we multitask. Before we get into tonight's topic, take a second to notice where you are. Are you in a bedroom, a car, a couch, a late-night kitchen with one lonely light on? Is it quiet around you, or is there the soft background noise of a city doing what cities do? And what time is it where you are right now? If you feel like it, picture the number on a clock without judging it. Early, late, or somewhere in the middle, it's still the same planet turning under you. Now, the idea we're exploring is simple to say, but it gets complicated the longer you sit with it. What if something was here before us, and we're only just starting to notice the possibility? Not before us, as in last century, or before recorded history, or even before the first cities. I mean before modern humans in any form you'd recognise. Before agriculture, before writing, before the first stone tools we can confidently point to and say, yes, those were made by people. The kind of before that makes your brain want to reach for a handrail. You might be thinking, come on, if there was something here before humans, we'd know. And honestly, that's a reasonable reaction. We're used to living in a world where evidence sticks around. A broken bottle can last longer than the person who dropped it. A plastic toy can outlive whole neighbourhoods. A city, even when it's abandoned, leaves behind roads, foundations, weird patterns in the soil, a shape on the landscape that shows up in satellite images. Human activity is noisy. It marks the planet. It feels permanent. But Earth is very good at making things look permanent right up until they aren't. Here's a small, everyday version of what I mean. Think about a footprint on a beach. It can look crisp and detailed for a while, like it's been pressed into wet cement. You can see the toes, the heel, the texture of the sand. If you didn't know any better, you could imagine it lasting all day. Then one wave comes in at the wrong angle, and it's gone. Not mostly gone, not faded, just erased, as if it never happened. Now scale that up from one beach to a whole planet, and scale the time up from minutes to millions of years. Add wind, rain, frost, rivers, landslides, volcanoes, and the slow-moving conveyor belt of plate tectonics that drags pieces of crust down and remakes them. Suddenly, the idea that traces can disappear isn't strange. It's the default. This is where the topic becomes interesting, because it sits in a place between imagination and geology, between archaeology and deep time. It isn't about insisting we've found Atlantis under the sea, or claiming a lost super-civilization built everything. It's about a quieter question. If there had been something on Earth long before us, an earlier civilization, an unknown intelligent species, or even just a long-lasting technological presence, would we actually expect to find clear evidence today? And if the answer is not necessarily, then a second question shows up right behind it. Are we even looking in the right ways? Or have we been trained by our own short human timeline to expect the wrong kinds of clues? If that feels like a big leap, we'll walk into it slowly. Tonight is not about forcing a conclusion. It's more like turning a stone over and seeing what's underneath, then putting it back gently. One of the reasons this question matters is that it challenges a comfortable story we like to tell ourselves. The story goes something like this. Humans are new, and everything meaningful started when we started. Before that, Earth was just waiting. There were animals, sure, and plants, and long stretches of time where nothing important happened, at least not in a way we can relate to. Then modern humans show up, and the real plot begins. That story is understandable, but it's also very human-centered. Earth does not organize itself around our arrival. The planet has been active for about 4.5 billion years. Modern Homo sapiens have existed for roughly a few 100,000 years. If you compress Earth's history into a single calendar year, Humans show up very late on December 31st. That's not a poetic way of saying it. It's just a good way to remember the scale. Our entire written history would be the last few seconds before midnight. So if we're asking whether something could have happened before us, we have to admit how much time there is for before to include. There's another reason this question has started to feel less like pure fiction and more like a serious thought experiment. We've learned, especially in the last couple of centuries, that Earth's past is not empty. It's full of extinct species, vanished ecosystems, and strange transitions that left only partial hints in rocks. Whole lineages appear and disappear, oceans shift, continents merge and break apart. The atmosphere changes, the climate swings, catastrophes happen, recoveries happen. And in the middle of all that, life keeps going, adapting, trying new strategies. If you've ever looked at a museum display of fossils from different eras, you've seen this in a physical form. One room might be full of marine creatures that seem almost alien, another full of enormous reptiles, another full of early mammals. None of those worlds were practice runs for us. They were complete worlds on their own, lasting far longer than human civilization has existed. Now, here's a gentle twist. We know those worlds existed, but we know them through fragments. Fossilization is rare. Preservation is selective. Most organisms leave nothing behind that becomes a neat fossil you can pick up and label. Even when there are fossils, the record has gaps. Some periods are well represented and some are like missing pages. So we already live with the reality that Earth can hold an enormous story and still only leave us scattered pieces. That's the baseline. From there, it's not a wild move to ask, what about traces of activity that aren't biological fossils? What about signs of behaviour, manufacturing, mining, building, burning or changing landscapes? We can detect some things that happened long ago, like ancient wildfires through charcoal layers, or changes in chemistry through isotopes locked in rock. We can find evidence of meteor impacts even when the crater is worn down. We can detect shifts in carbon levels that suggest massive changes in life and environment. Those are all signals. Earth stores signals. But Earth also edits its own storage system. Imagine you keep a journal, but every week you spill water on it, tear out a few pages, rewrite others, then bind it back together with a different cover. In the end, you still have a book, and you can still read parts of your past, but it's not a clean record. It's a record that has been constantly revised by accidents and repairs. That's closer to how geology works. So when people hear the idea something might have been here before modern humans, the most useful response is not immediate belief or immediate dismissal. The useful response is curiosity combined with a practical question. What would be left and where would it be? If you're feeling skeptical, keep that skepticism. It's healthy. It helps. This topic attracts exaggerated claims, and we're not here for those. But skepticism is most powerful when it's paired with a willingness to consider what the evidence would even look like. Otherwise, it can turn into a reflex instead of a tool. On the other side, if you're feeling excited, like this sounds mysterious and thrilling, keep that too, but let's keep it grounded. The most interesting version of this idea isn't about secret ancient empires with perfect knowledge. It's about how easily the planet can erase ordinary things, and how our perspective shifts when we stop assuming that no evidence automatically means nothing happened. Let's do a simple mental exercise that stays close to real science. Suppose a civilization like ours existed, not 10,000 years ago, but 10 million years ago. Not necessarily humans, just a species with technology, industry, the ability to build and extract resources. How long would their roads last? How long would their buildings stand? If they had metal bridges, would those survive? Would plastics remain? Would their landfills leave a signature? Would their mining scars still show? Some answers are straightforward. A metal bridge rusts, a building collapses, plants grow over it. Erosion smooths it out, rivers change course, sediments bury the remains. After enough time, the structure becomes a layer, then a distorted layer, then a mineralized patch, then part of the rock, then maybe subducted into the mantle and gone entirely. Other answers are less obvious. Some materials are very durable, and some chemical signals can persist. Certain industrial processes leave distinctive isotopic fingerprints. Burning large amounts of fossil carbon changes the ratio of carbon isotopes in the atmosphere, and that signal can show up in sedimentary records. Some pollutants, like certain heavy metals, can accumulate in layers. Even plastics, while they break down, can leave microplastics and altered chemistry in sediments, at least for a while. But for a while is the key phrase, because a while on Earth can be both shorter and longer than we intuitively expect. Some signals last centuries, some last tens of thousands of years, some might last millions under the right conditions, and some vanish quickly. It becomes a question of conditions and storage. For example, the ocean floor is constantly being created and destroyed. New crust forms at mid-ocean ridges, and old crust gets subducted. Most of the seafloor is geologically young compared to continents. That means if an ancient civilization existed mostly along coasts, like ours tends to, it might have left a lot of traces in regions that are now underwater, and many of those underwater regions might not preserve anything long-term, because the crust itself gets recycled. Meanwhile, certain environments are better at preserving. Rapid burial in sediments can protect things. Low oxygen conditions can slow decay. Stable cratons, very old stable parts of continental crust, can hold ancient rocks for a long time. Deep caves can preserve bones, art and artifacts for tens of thousands of years. But millions? That's a much tougher ask. So the question isn't just, could something have existed? It's also, could its evidence survive? And would we recognize it? Recognition matters more than it sounds. Think about how many times people have found something unusual in nature and misinterpreted it at first. Strange rock formations that look like tools but are natural. Fossils mistaken for stones and stones mistaken for fossils. Even today, with all our instruments, we still argue about certain marks on ancient bones. Were they made by tools or by natural processes? Were they made by predators or by humans? These debates happen within the last few million years, not hundreds of millions. Now imagine a trace that has been crushed, heated, dissolved, reformed, and chemically altered. Even if something survived, it might survive in a form that doesn't look like a thing. It might be a chemical anomaly, a layer with an unusual composition, a pattern in isotopes, a concentration of certain metals, something that reads more like a medical test result than like an artifact. That's one reason scientists approach this topic as a thought experiment instead of a treasure hunt. It's not about finding a single dramatic object that proves everything. It's about asking what kinds of signals would remain, and whether any known signals in Earth's past could be consistent with industrial activity, large-scale land use, or other markers of a technological species. And that leads to an even more practical question. Have we ever seen anything like that? There are moments in Earth history where the record shows abrupt changes, sudden warming events, carbon isotope shifts, mass extinctions, rapid changes in sedimentation. Sometimes those are explained by volcanism, methane release, asteroid impacts, or changes in ocean circulation. Those explanations are often convincing, and they're based on evidence. But what this topic adds is a new kind of lens. If a technological species existed and changed the planet, what would their signature resemble? Would it look like volcanism? Would it look like a climate shift? Would it look like a strange spike in certain chemicals? This doesn't mean we should relabel natural events as ancient factories. It means we can broaden the catalogue of hypotheses we know how to test. A lot of science progresses that way. Someone asks a question that sounds a little strange, and then the field gets better at describing what would count as evidence either way. The real value is in sharpening our methods, not in chasing a particular outcome. So when you hear something was here before us, try to hold it like this, not as a claim, but as a prompt to think carefully about preservation, detection, and scale. And there's another layer here that's almost comforting, in a strange way. If Earth could erase an earlier presence so thoroughly that we only have faint hints, then it highlights how temporary our own marks might be in the long run. We tend to think of ourselves as leaving an indelible footprint. We talk about a permanent human impact. In the short term, that's true. Our impact is huge. We change landscapes, chemistry, ecosystems. But in the long view, Earth is relentless. It buries, grinds, melts, and recycles. That doesn't let us off the hook for what we do now, of course. Short-term damage is still real damage, especially to living systems that have to survive it. But it does place our existence into the same vast frame as everything else that lived and changed and vanished. If you're getting sleepy, this is a good moment to let your attention soften. You don't have to hold every detail. The main idea can sit in the background. Earth has a long memory, but it's not a perfect memory. Now, because this is just about Earth, we'll keep our feet on the ground. We're not going to leap to dramatic conclusions. We're going to start with the simplest version of the question and build outward, using what we already know about the planet. Here's where we'll begin. What does it even mean to say before us on a planet that constantly reshapes itself? What counts as evidence when the recorder is also the editor? And if something did exist long ago, why would the traces be so hard to find? If you're enjoying this kind of calm exploration and you'd like more episodes like it, you can like the video and subscribe. It helps the channel reach people who might be listening in the same quiet way you are. You don't have to do it right now if your hands are busy or you're already getting comfortable. Just keep it in mind for later, like a sticky note you don't have to read immediately. Alright, settle in as best you can. Let your shoulders drop a little, unclench your jaw if you notice it's tight, and take a slow breath that doesn't feel forced. There's no test at the end of this. We're going to walk into the next idea gently, starting with the planet's talent for erasing its own past, and why that matters so much when we ask whether an earlier presence could have existed at all. If you stayed with me from the last stretch of this conversation, you might notice something funny about the idea we're holding. It sounds dramatic when you say it out loud, but it arrives in the mind very quietly. It doesn't usually announce itself with trumpets. It tends to show up the way a small doubt shows up when you're sure you locked the door, and then, halfway down the street, you can't quite feel the certainty anymore. You turn it over once, tell yourself it's nothing, and then later, when things get quiet, you turn it over again. That's the feeling behind the question of whether someone, or something, could have been here before us in a way we would recognise as purposeful, organised, and long-lasting. Not just life, because we already know life was here long before us, in forms more varied than we can comfortably picture. The question is narrower and also stranger. Could there have been an earlier presence that shaped the world in ways beyond ordinary biology? And could that presence have faded so completely that we only get the faintest hints? If you're listening from a place that's already dim and comfortable, let the question sit lightly. You don't have to answer it. You don't even have to decide whether you like it. Just notice how your mind reacts. Some people feel immediate skepticism, like a mental hand going up to stop the conversation. Some people feel a quick spark of excitement. Some people feel a mild unease because the idea nudges at a familiar comfort, that we know what the past was and that our place in it is clearly marked. There's a reason this suspicion appears at all, and it doesn't come from nowhere. It's partly because of how often we've underestimated the past, even on much shorter timescales. Not that long ago, in the big view, many educated people believed human history was shallow, that civilization was only a few thousand years old in any meaningful sense, and that prehistoric humans were basically the same everywhere. Small groups, simple tools, no large structures, no complicated social systems. Then archaeology kept doing what it does best, making confident stories feel temporary. Sites were found that didn't fit the timeline people expected. Dates were pushed back. complexity showed up earlier than assumed. Whole categories of human behaviour that were thought to be late turned out to be older. When you learn that lesson a few times, the mind becomes cautious. It starts to wonder what else might be sitting outside the spotlight of what we've already confirmed. A second reason is even simpler. Earth is full of things that look like traces. Walk through a forest and you'll see patterns that feel intentional. A line of stones that looks like a boundary. A circle of trees that looks like it was planted. A smooth groove in rock that resembles a cut. Visit a beach and you might find a piece of driftwood shaped like a tool. Hike in the desert and you'll notice dark streaks on pale stone that look like brushstrokes. The world produces shapes that resemble human actions, and our brains are very good at spotting those resemblances. It's the same reason you can see a face in the front of a car or in a cloud without trying. This pattern matching ability is not a flaw. It's one of the ways humans survived. The problem is that it doesn't switch off when we deal with deep time. It keeps suggesting meaning even when meaning may not be there. So one strand of the suspicion is psychological. We're wired to see someone did this, even when nature is perfectly capable of doing it on its own. But there's another strand, and this one is more grounded. It comes from how uneven our access to the past really is. Think about what it takes for something to be known. It has to exist in a form we can detect. It has to remain in place long enough. It has to survive damage. It has to be discovered, and then it has to be recognized for what it is. That last part is not trivial. Recognition depends on context and expectation. If you don't expect a certain kind of thing to exist, you may not interpret it correctly even if it's right in front of you. A simple example, if you found a perfectly round metal disc on a hiking trail, you'd probably assume it came from a machine or a piece of equipment. If you found a naturally formed round stone, you might assume it was shaped by water or wind. The object matters, but so does the story you already have in your head about what is likely. Now magnify that issue. Imagine you're studying a sediment layer that is, say, 80 million years old. You find a thin band where the chemistry is odd. Maybe there's a spike in some metal, or an unusual ratio of isotopes. You have 100 possible natural explanations, from volcanic ash to changes in ocean circulation, to a shift in the organisms that were living at the time. The idea that the anomaly could be linked to technology is so far outside the normal set of assumptions that it barely registers as an option. Not because scientists are closed-minded, but because science builds models from what has evidence, and it prioritizes explanations that match known processes. That's exactly how it should work. It's the reason we have reliable knowledge at all, but it means something important for this topic. If an earlier presence left traces that don't look like statues or buildings, and instead look like subtle chemical patterns, then we might have spent a long time simply filing those patterns under natural variation, or unknown cause, without asking a different kind of question. So the quiet suspicion is partly the recognition that the past is accessible only through a narrow window, and the window's shape is determined by geology, preservation, and our own habits of interpretation. Another way to approach this without getting carried away is to think about how you would detect our own civilization if you weren't here and if you came much later. If an intelligent species visited Earth 1 million years from now, what would they see? They might see strange layers in sediments. They might find concentrated pockets of certain materials. They might detect an unusual carbon signal. They might find fragments of synthetic compounds. They might notice extinction patterns and abrupt shifts in ecosystems. They might find a few durable objects in unusual places, like deep ocean sediments or protected caves. What they probably would not find, at least not in a way that looks like a modern skyline, is New York City sitting there waiting to be admired. They would not drive down a highway that still has lane markings. They might not find recognizable bones in most places, because bones don't usually last that long unless conditions are right. They would be reconstructing us through hints. And if that's true for 1 million years, then it becomes even more true for tens of millions. At that point, you can see why someone might start to wonder whether the absence of obvious artifacts is really a decisive argument. Not proof, not a reason to believe, but but a reason to keep the door slightly open. Now, it's worth taking a breath here, because there's a delicate line we're walking. The question, could something have been here before us, easily slips into I can explain everything mysterious with that idea. That's not what we're doing. In fact, one of the most calming ways to handle this topic is to notice how much is already explainable without reaching for extraordinary answers. People have long pointed to puzzling structures and said, this must have been built by someone far more advanced. In many cases, the reality is that humans are more capable than modern stereotypes assume. Stonework that looks impossible was often achieved with patience, organisation, and techniques that are clever but not supernatural. Ancient people were not naive. They experimented, they learned, they passed knowledge on. They were engineers in their own context. So, if you ever feel your mind drifting toward everything ancient is evidence of something unknown, you can gently steer it back. We don't need that. The interesting version of this topic doesn't require turning normal archaeology into a mystery story. The more reasonable place to focus is deeper time, beyond the range where human artifacts should exist at all, and toward the kinds of signals geology can carry forward. That brings us to a different kind of question, one that changes the emotional tone a little. Instead of, was there a lost civilization like ours, we can ask, what forms of intelligence could exist on Earth and leave only faint traces? Modern humans are only one example of intelligence. We tend to treat our version as the default, because it's what we know from the inside. But intelligence is not a single thing. It's a set of capabilities, and it can show up in many shapes. Some animals use tools, some solve puzzles, some communicate in complex ways, some build structures, some cooperate on large scales. Humans combined many of these traits with language, long-term planning, and the ability to transmit detailed information across generations. That combination produced technology and large societies. Now imagine a different combination. Imagine an intelligent species that never discovered fire in a sustained way, perhaps because of environment or biology, but that still altered its surroundings through other means. Or imagine a species that lived primarily in the ocean, where stone structures don't last the same way, and where metallurgy is more difficult. Or imagine something that built with materials that biodegrade quickly, like living plants or organic composites, leaving almost no durable remains. Even without getting too creative, you can see how many pathways could lead to something happened without leading to the kind of evidence we're trained to look for. And then there's an even more basic scenario, which is not civilization, but activity. A species could mine a specific resource for a few thousand years, then go extinct. A species could burn fuel and alter the atmosphere briefly, then vanish. A species could spread across certain regions and create soil changes, then be wiped out by climate shifts. None of these require a long, stable, globe-spanning empire. They require time, population, and a set of behaviours that produce measurable effects. If you're thinking, but wouldn't we see the fossils? Remember that fossilization is selective. Most organisms do not fossilize. Most landscapes are not good at preserving what lived on them, and even when fossils exist, they are often discovered only because we happen to dig in the right place at the right time. We know dinosaurs well partly because they had hard bones, and because certain sedimentary environments preserved them. For many other lineages, we have a handful of fragments and a lot of inference, so the suspicion can take a humbler form, not there was definitely something, but Earth's record is incomplete enough that it's hard to rule out every possibility. What makes this humbler form worth discussing is that it connects to a real scientific habit. Scientists are cautious about claiming absolute certainty in complex systems, especially when the data is fragmentary. A good scientist can say, we have no evidence for X, and also say, our ability to detect X is limited, so absence of evidence is not the same as evidence of absence. That's not a trick, it's a statement about measurement. In everyday life, we forget how often we rely on indirect evidence. You don't see the wind, but you see trees move. You don't see the past, but you see layers in rock. You don't see extinct animals in motion, but you see their footprints, their bones, their teeth marks, their nests. The story is built from traces. When the traces are sparse, the story becomes less certain. That's the quiet space this topic lives in. Let's bring it down to something more concrete again, because staying in the abstract, in the general, can make the mind spin. Here's a practical way to think about it that doesn't require belief in anything unusual. On Earth, there are places where the surface is young. River deltas shift constantly. Floodplains rewrite themselves. Coastlines move. Volcanic regions lay down fresh rock. Glaciers scrape landscapes clean. If a city existed in a place like that and then disappeared, it could leave little behind in a surprisingly short time. On the other hand, there are places where the surface is old and stable, where rocks have been exposed for long periods and the pace of change is slow. Those places can preserve things longer, but they also tend to be harsh environments where building and maintaining a large society might be difficult. So, even within the last few tens of thousands of years, preservation is uneven. Now extend that unevenness into deep time, where continents shift and oceans come and go. The result is that there may be huge stretches of Earth's history where the most obvious evidence, if it ever existed, is simply gone. This doesn't mean evidence is impossible. It means the evidence may be of a kind we don't instinctively picture. For example, if you dig into ancient sediments and find a layer rich in a certain industrial pollutant, that could be a clue. If you find an isotope ratio that suggests large-scale combustion of certain carbon sources, that could be another clue. If you find unusual concentrations of certain metals that are rare in nature, but common in industrial waste, that could stand out. If you find a sudden, sharp boundary where ecosystems shift in a way that looks like rapid pressure rather than slow change, that could be a signal worth examining closely. Notice what's missing in that list. Pyramids, statues, roads, and written records. The suspicion becomes less about hidden monuments and more about the planet's chemistry and sedimentary memory. There's also a reason this topic shows up now, in our time, rather than in centuries past. We've reached a point where we can measure Earth in finer detail. We can detect tiny changes in isotopes. We can scan with satellites. We can model climate in deep time. We can drill cores through ice and sediments and read layered histories. In other words, we've developed senses beyond our eyes and hands. When your senses expand, your questions expand. It's the same pattern that happened when microscopes became common. Suddenly, there was a whole world of life we didn't know existed, not because it suddenly appeared, but because we finally had tools that could detect it. So part of this modern curiosity is simply a natural response to better measurement. If the world is full of signals we couldn't detect before, what might we have missed? At this point you might wonder where the emotional pull of the idea comes from, because it's not just scientific, it touches something human. One part of it is humility. The thought that we might not be Earth's first significant presence can feel like an ego check, and sometimes that's uncomfortable. Another part of it is loneliness in an odd way. If you've ever looked at the night sky and wondered whether anyone else is out there, the idea that Earth itself could have hosted something earlier feels like the same question pointed inward instead of outward. Not aliens, not distant stars, but our own ground holding older secrets. And then there's the simplest part, curiosity. Humans are story-making creatures, and the biggest story we have is, how did we get here? It's normal for the mind to test alternative versions of that story, especially when the official version still has gaps. Even the best scientific account has unknowns, because science is always in progress. It's honest about what it doesn't yet know. If you're listening and you feel your thoughts drifting, that's fine. You can let them drift. This topic invites wandering because it sits on the edge of what we can confirm. Before we move further, I'll add a small, gentle reminder. If you like this calm way of exploring strange questions, you can subscribe to Just About Earth. It's one of those simple actions that supports the work without demanding anything from you in return. If that's not your thing, No problem at all. You can just keep listening and let the ideas pass by like scenery. Now, let's anchor again on the main point of this stretch. The suspicion isn't a claim. It's a recognition that the planet is old, that the record is incomplete, and that what we'd consider obvious evidence might not survive the kinds of processes Earth does routinely. And that takes us naturally toward the next thing we need to understand if we're going to handle this question responsibly. Earth's talent for erasing. Because once you accept that the planet is not a museum that keeps every exhibit intact, you start to see how quickly even big things can disappear. Mountains wear down, seas advance and retreat, rivers cut canyons and then fill them, whole regions get buried, heated and transformed. The ground beneath us is not just a surface, it's a moving system. So, rather than asking, why haven't we found the ruins, the better question becomes, what does Earth do to ruins over long time? And what kinds of traces can survive that treatment? Let that be the next thought you hold loosely as you settle more comfortably wherever you are. What time is it for you now? And if you imagine the planet turning through millions of years the way a clock turns through minutes, can you feel how much gets smoothed, folded and forgotten along the way, even when something real once stood there? It helps, I think, to start with a simple image that doesn't ask you to believe anything unusual. Picture a city you know well, but empty. No people, no maintenance crews, no lights turning on at dusk. The doors are left ajar. The traffic signals freeze on whatever colour they happen to be showing when the last electricity faded. At first, the place would still feel like itself. Streets would still have names. Buildings would still have straight edges. You could still recognise the purpose of everything. This was a school, this was a hospital, this was a grocery store, this was a bridge. Then the first small changes would begin, and they would not be dramatic. Water would get into places where water always wants to go. It would slip into cracks in concrete and along seams in asphalt. Plants would take advantage of tiny pockets of soil that collect in corners. Birds and insects would move in. Rust would spread. Paint would peel. The city would start to look slightly tired, like a room that hasn't been cleaned in a while. If you've ever left a bicycle outside for too long, you already know the basic lesson. It doesn't need a hurricane. It doesn't need a war. It just needs time and weather, a little moisture, a little sun, a little freeze and thaw, and the smooth surfaces start to become rough. The object becomes less made and more found. Over a few decades, roofs would begin to fail. Over a century, the easy-to-break parts would collapse. Over a few centuries, trees would push through walls that once looked permanent. Over a few thousand years, many of the higher structures would be flattened into heaps, and those heaps would begin to blend into the ground, especially in places where sediment builds up. A river that had been politely kept inside its channel would wander back into the city and start rearranging it like it was just another floodplain. It's useful to imagine that slow ruin, because it gives you a sense of what erasure looks like up close. Earth does not usually erase things with a single dramatic act. It erases with routine, and that routine is the reason the big question we're exploring can't be answered by intuition alone. Our instincts are trained on short time. We live inside a narrow window, where a building can feel ancient at 300 years old, and where a stone monument feels permanent because it was built 2,000 years ago and is still standing. That makes sense from a human point of view. 2,000 years is a long time if you have a human lifespan. But to the planet, 2,000 years is a brief pause. Earth has several different ways of clearing the surface, and it can use them in combination. The first one is the most familiar, weathering and erosion. Wind, water, ice and gravity are always at work. Rain falls, collects, flows downhill, carries particles and cuts channels. Water freezes and cracks and expands, prying rocks apart one grain at a time. Heat makes materials expand, cold makes them contract, and repeated cycles fatigue. Solid surfaces the way repeated bending fatigues a piece of metal. Wind picks up sand and turns it into a quiet sandblaster. Gravity pulls on slopes and eventually wins. whether that looks like a gentle creep of soil or a sudden landslide. If you're listening and you have ever watched a small stream after heavy rain, you've seen a miniature version of how powerful water can be. It doesn't need to be a raging river. A thin sheet of water moving across a path can carve little channels and move surprising amounts of sand and grit. Now extend that across a continent and across hundreds of thousands of years. The landscape becomes something like a slow conveyor belt, grinding high places down and carrying the pieces away. This alone is enough to bury and disperse a lot of evidence. A city reduced to rubble becomes a scatter of materials. Those materials get mixed with soil carried by water, broken down chemically and redistributed. In some climates this happens fast. In others it happens slowly, but it happens. The second method is deposition, which is less dramatic and sometimes more effective. Deposition is the act of covering. Rivers bring sediment and lay it down in deltas. Floods spread silt across plains. Dust settles over everything. Landslides pile material in new places. Volcanic ash blankets regions in a layer that can be meters thick. Over time, layers stack up. If you want something to disappear from view, one of the simplest ways is to cover it. Covering can actually preserve things for a while, like a blanket can protect something fragile. Buried objects are shielded from some weathering, but burial also hides. An entire landscape can become a new surface, and the old surface becomes a chapter in the rock pressed and altered. This is already enough to explain why we don't find clear traces of even relatively old human settlements in many places. They're there, but they're not on the surface anymore. Archaeology often works because people know where to dig, or because construction accidentally reveals layers, or because the landscape has stayed stable enough to keep things close to the top. When you begin talking about millions of years, the third method becomes the main character: tectonics. The surface of Earth is not one solid shell that politely keeps everything in place. It is a set of plates that move. They collide, they pull apart, they slide past each other. They create mountains and trenches. They raise seabeds into dry land and sink dry land underwater. They do this slowly, but they never stop. If you want to understand why deep-time ruins are unlikely to survive, you can think of plate tectonics as Earth's recycling system. The ocean floor in particular is constantly being renewed. New crust forms at mid-ocean ridges, and older crust is eventually subducted back into the mantle. That means much of the seafloor is relatively young compared to the age of the planet. It's as if the ocean is constantly deleting and rewriting its own storage. This matters because coastlines are where a lot of activity tends to concentrate. Even in our own world, coasts are where many large cities exist. Rivers meet the sea. Trade becomes easier. Climate can be more moderate. If a hypothetical earlier civilization had similar preferences, a lot of its evidence would end up in places that are vulnerable to sea level changes and to the recycling of oceanic crust. After enough time, much of that evidence could be dragged down into the mantle and removed from the reachable record entirely. That's not a dramatic claim. It's a basic feature of how the planet works. The Earth literally eats its own surface in some places. Then there's metamorphism, which is the quiet internal part of the eraser. If something is buried deep enough, pressure and temperature change it. Rocks get squeezed, heated, and transformed. Minerals rearrange. Original textures can be lost. Chemical signatures can be altered. A layer that once held distinct grains and fragments can become a more uniform crystalline rock. Whatever it contained becomes harder to interpret. You can think of it like putting a detailed drawing in an oven, then compressing it under weight. The paper might still exist as material, but the ink lines blur, and then they're gone. The information that mattered is what disappears first. Even without tectonics, there are other forms of erasure that are surprisingly thorough. Glaciers, for example, are not just ice sitting there. They are moving bodies that scrape and pluck and grind. A glacier passing over a landscape can remove soil, polish rock, and transport huge boulders far from their origin. If you had built something on a surface that later became glaciated, the glacier could wipe it out like a giant piece of sandpaper. In many places, glaciers have already erased older surfaces and left behind landscapes that look fresh in geological terms, even though they're ancient in human terms. Coastlines can be just as aggressive, in a different way. Waves constantly attack edges. Sea levels rise and fall over time, exposing land and then drowning it again. The sea can also bury. It can lay down sediments that cover what once was land. So coastal evidence can be both destroyed and hidden, depending on the phase. Rivers are another slow, relentless editor. They don't just sit in one place. Over long time, they migrate. They cut down, then later they fill. They meander, abandon channels and build new ones. A site that was once stable ground can become part of a floodplain, then part of a riverbed, then part of a terrace, then part of a valley wall. If you've ever looked at an aerial photograph of a river with looping curves and cut-off oxbow lakes, you're looking at a system that loves to rearrange itself. Give it tens of thousands of years, and it can dramatically reshape the landscape. Give it millions, and it can erase almost everything that was superficial. There's also biology, which sounds gentle but is one of the most powerful forces of change on the surface. Roots crack rocks. Burrowing animals churn soil. Microbes break down materials. Forests create thick soils that can bury features and mix layers. Termites and worms and ants can move incredible amounts of sediment over time. This churning process, called bioturbation, is like a constant stirring of the shallow record. For archaeology, it matters because it blurs layers. For deep time, it matters because it can erase delicate traces even before other processes have a chance. If you've ever seen a garden bed after a year, you know how quickly the surface becomes mixed. Things you put in a certain place end up elsewhere. Now imagine that mixing happening continuously over thousands of years, and then add floods and sedimentation on top of that. So what does this mean for civilizations in the deep time sense? First, it means that the kind of evidence we instinctively imagine is unlikely to survive. The things we picture, buildings, monuments, roads, are surface features. They depend on being at the surface to be recognizable. The surface is where the eraser works hardest. Second, it means that even if something survives physically, it may not survive in a recognizable form. An old concrete foundation could be dissolved and reprecipitated as different minerals. Metal could corrode and disperse. Glass could break and weather. Plastics could fragment, oxidize, and become part of sediment in ways that don't look like plastic after enough alteration. Third, it means that time doesn't just remove objects, it removes context. Context is what makes an artifact obvious. A single-shaped stone means little without a pattern around it. A fragment of metal means little without an understanding of where it came from and how it got there. Even if a future observer found something made by us, that observer might not immediately see this was a city. They might see this as a layer with strange chemistry and unusual concentrations of certain materials. At this point you might wonder, if Earth is so good at erasing, how do we know anything about the past at all? That's a comforting question, because the answer is that Earth also preserves, but it preserves selectively. Think of the planet as a library that keeps some books in perfect condition, loses others entirely, and in some cases only keeps a few torn pages that are smeared with water stains. Fossils are preserved under certain conditions. Sedimentary layers can keep records of environments. Ice cores can preserve atmospheric snapshots for hundreds of thousands of years. Rocks can keep chemical signatures for far longer. The record exists, but it is not evenly distributed across time and space. In practice, the past survives best when it's quickly buried and then protected from later disturbance. That's why we have rich fossil deposits in some places and almost nothing in others. That's why certain ancient footprints are preserved. They were made in soft sediment, quickly covered, and later turned into stone. If that covering hadn't happened, the prints would have been erased in days. So if you're thinking about whether an earlier presence could have left traces, you start to realize that the question is not simply, Would it leave something behind, but would it leave something behind in one of the places that geology happens to protect? It's a little like dropping a message in a bottle into the ocean, and then asking whether someone will find it. The ocean is huge, and the bottle can break, sink, or be swallowed by sand. Yet some bottles do wash up because conditions line up. The fact that some messages survive doesn't mean most do. Now bring your attention back to the idea of a technological species, because that's where the conversation tends to drift. Technology doesn't only mean skyscrapers, it means energy use, resource extraction, manufacturing and waste. The more a society depends on altering raw materials, the more it tends to leave behind chemical traces. That's not a moral statement, it's a mechanical one. You take something from the ground, you move it, you concentrate it, you transform it, and the transformation often has side effects that show up as unusual patterns. If you're still awake enough to smile, consider this. One of the most durable things humans produce might not be our art or our architecture. It might be our trash, and even that isn't guaranteed. Landfills can be buried and then altered. The materials can be broken down, scattered, and incorporated into rock. In deep time, a landfill might become a thin, chemically distinct seam, not a recognizable heap of objects. This shifts the idea of ruins. The ruins that matter in deep time may not look like collapsed buildings. They may look like a change in the chemistry of sediments across a boundary. They may look like a brief spike in certain compounds. They may look like a strange layer of ash and soot, or an unusual pattern of isotopes that suggests a large-scale shift in carbon cycling. Here's where the eraser becomes almost too effective, because it introduces another problem. If the evidence is subtle, it can be confused with natural processes. Volcanoes also release carbon. Natural wildfires also create soot. Certain geological events can concentrate metals. Ocean chemistry can shift. Climate can change rapidly for reasons that have nothing to do with intelligence. So even when Earth preserves, it does not label. It stores signals without telling you what caused them. This is why the best way to think about Earth's erasing power is not as a magical disappearance trick, but as a filter. The filter removes most surface detail quickly, keeps some buried detail for longer, and sometimes distorts what remains. Over millions of years, the filter becomes very strict. Only certain kinds of information make it through. If you're listening from somewhere comfortable, you can let that idea settle. Earth is an active system that both records and edits. It's not a vault. It's not a museum. It's a machine that runs. There's a soft kind of humour in this if you want it. We tend to treat our works as though they are permanent, as though we are engraving ourselves into the planet. Yet if you zoom out far enough, Earth behaves like a person tidying up after a party. It doesn't do it immediately. It waits. It lets the mess sit there for a while. Then slowly and inevitably, it starts clearing things away. First the fragile stuff goes, then the obvious stuff. Then eventually the traces become so faint that you need special instruments and careful reasoning to detect them at all. If you're wondering where that leaves us with the original question, this is the key point. The planet's ability to erase makes it difficult to rule out an earlier presence based solely on the absence of obvious ruins. That isn't the same as saying an earlier presence existed. It's saying that no statues found is not the right standard for deep time. What is the right standard? That's where things get more technical, and, in a way, more interesting. Because once you accept that Earth deletes surface detail, the question becomes, what kinds of traces could survive the deletion process? What materials and signals have the best chance of making it through? What time windows and environments are most likely to preserve evidence? And if an earlier presence did exist, what would we realistically expect to find today? Not in a movie sense, but in a sediment core sense. You might want to check in with yourself here. Where are you listening from now, and has your body settled a little more since we started? If it's late where you are, you don't have to keep a tight grip on the details. The important thing is the direction of the thought. Earth erases in predictable ways, and that predictability tells us what kinds of proof are possible. Because once the eraser has done its work, the challenge isn't only that the evidence is missing, the challenge is that the evidence that survives may not look like evidence at first glance, and it may be scattered across the planet in forms that require patience to interpret. That leads us toward the next practical problem. If you wanted to test the idea seriously, what would you even look for, and how would you tell it apart from the planet's own natural signatures as it writes, rewrites, and continues moving forward? So now we're standing in a slightly uncomfortable but useful place. We've admitted that Earth is very good at erasing surface detail, and that it doesn't do it out of malice or mystery, but because it's a working planet with weather, water, ice, and moving crust. Once you accept that, you run straight into the next hurdle, and it's the hurdle that decides whether this whole idea stays in the realm of late-night speculation or becomes something you can actually test. What would count as proof, and what could possibly survive for millions of years? This is where a lot of conversations about something before us quietly collapse. Not because the idea is automatically wrong, but because people picture evidence in the wrong form. They imagine a stone city still intact, sitting politely on a hill waiting for a drone to fly over it. They imagine a metal artifact gleaming in sunlight. They imagine a carved message in a cave that somehow avoided being covered, flooded, or ground into dust for 50 million years. Those images are entertaining, but they don't match how preservation usually works. Deep time does not play nicely with neat displays. If you're listening late, you don't have to hold every detail in your head. Just keep one question warm in the background. If something happened long before humans, would it leave anything that we could still detect? And if it did, would we recognize it as unusual? The hardest part about proof in this context is that it's not a courtroom situation where you bring one decisive object and the case is closed. It's more like medical testing. You rarely get one single number that tells you everything. You get a pattern across different measurements. You get signals that are suggestive but not perfect. You get results that need context. You get false positives and false negatives. And you have to ask, very carefully, whether there are simpler explanations that fit the same data. That's not a weakness. That's what careful thinking looks like. So let's talk about the kinds of things the planet can preserve and what happens to them over huge spans of time. The first category is physical objects, the kind we naturally call artifacts. Tools, buildings, machines, roads. These are what most people mean when they imagine evidence of an earlier presence. The trouble is that artifacts are mostly surface dependent. Their meaning comes from shape, placement, and association. A stone wall is recognizable as a wall because the stones sit in a pattern that isn't typical of natural rockfall. A road is recognizable because it's flat, continuous, and engineered. A machine part is recognizable because it has edges, holes, and consistent manufacturing marks. Those features are exactly what erosion, weathering, and burial tend to destroy first. Even if the materials survive as material, their information content gets scrambled. A road turns into gravel mixed into soil. A wall turns into a scatter of stones that looks like a natural slope deposit. A metal object turns into oxides that spread through surrounding sediment. A concrete foundation becomes a patch of altered chemistry that might not resemble concrete anymore. That doesn't mean physical objects can't survive. It means they survive best under special conditions, and those conditions are rare at the scales we're talking about. For example, we sometimes find remarkably preserved things from tens of thousands of years ago because they were quickly buried and protected. Bones in caves, tools in stable sediments, footprints sealed under layers, wooden objects preserved in low-oxygen wetlands. That's already impressive. But millions of years is a different level. Over millions of years, the probability that any one object stays intact and stays accessible drops sharply. It's not zero, but it's not the place you'd put your hopes if you were trying to design a serious search. If you want to think of it plainly, the surface is like a busy sidewalk. Anything left on it gets kicked, stepped on, washed away, picked up, or ground down. If you want something to last longer, you have to get it off the sidewalk and into storage. On Earth, storage usually means sediment, and sediment has its own rules. So the second category is buried remnants. Not necessarily intact objects, but things trapped in sediment layers that later become rock. This is where the conversation becomes more realistic. Sediments can preserve outlines, fragments, and chemical traces. Sediments also preserve time in a way the surface does not. Layer on layer, with older layers below and younger layers above. It's not perfectly orderly, but it's often orderly enough to reconstruct sequences. Now, if you're imagining a civilization being fossilized, it's important to adjust the mental picture. Fossilization, in the broad sense, means information about something gets locked into rock. That information can be a body fossil like a bone, but it can also be a trace fossil like a footprint, a burrow, a nest, or a bite mark. It can be a chemical signature. It can be a change in sediment composition. It can be a layer of ash. The fossil record is not just a graveyard, it's a record of interactions with environments. So if an earlier presence existed and interacted with the environment in a consistent way, that interaction might show up as a trace-like signature rather than a tidy object. Instead of, here is a building, it could be, here is a layer that contains an unusual mixture of materials, or here is a sudden change in certain chemical ratios, or here is evidence that a landscape was disturbed at large scale. This is where the idea becomes testable in principle, because geologists and earth scientists already know how to read layers. They already measure isotopes. They already look for anomalies. The method would be to ask whether any anomalies match patterns that would be difficult to produce naturally. But that immediately leads to the next problem. Nature can produce a lot of strange patterns. Volcanoes can spread ash across continents. Massive flood basalts can change climate and chemistry. Meteor impacts can create spikes in certain elements. Ocean circulation changes can shift carbon signals. Wildfires can produce soot layers. Even biological changes can alter sediment composition in dramatic ways. So the challenge is not simply finding something odd, it's proving that odd is not explainable by known natural processes. At this point, it helps to list the kinds of signatures that might survive longer than physical artifacts, without turning it into a checklist you have to memorize. Think of it as a set of broad buckets. One bucket is long-lived chemical fingerprints. Chemistry can persist because it becomes part of minerals or becomes part of the bulk composition of rock. If a process changes the ratio of isotopes in carbon, oxygen, nitrogen, sulfur, or other elements across a large region, that shift can remain detectable for millions of years, especially in sediments that aren't later melted or heavily altered. Isotopes are useful because they behave like labels. They don't tell you a story by themselves, but they tell you something changed in the cycling of an element. Here's a simple example from everyday life. If you sweeten tea with sugar, you can't easily separate the sugar back out, but you can measure that the tea is sweeter. In a similar way, if something injects a lot of carbon with a particular isotopic flavour into the atmosphere and oceans, you may not find the original carbon source sitting there in a jar, but you can detect that the overall mix changed. A second bucket is unusual concentrations of elements and compounds. When humans do industry, we concentrate things. We dig up metals, refine them, distribute them, and discard them in patterns that don't match most natural background levels. Even without assuming anything dramatic, a technological species would likely leave behind some concentrated waste streams. Certain metals that are rare in average crust can become locally abundant around industrial activity. Some synthetic compounds are unusual in nature. Some kinds of soot and combustion products have distinctive forms. The catch is that over millions of years those concentrations can disperse, react, dissolve, and reform. The signal might remain, but it might be muted and smeared across layers, and again, geology can create concentrations too through hydrothermal activity, mineral deposits, and sediment sorting. You would need a pattern that looks less like one weird spot and more like a broad, consistent fingerprint. A third bucket is structural changes to sediments. Large-scale land use can change erosion rates. It can change how much sediment rivers carry. It can change the composition of sediments reaching the ocean. Even natural events do that, like glaciations and mountain building. But the point is that a major shift in how landscapes shed material can be recorded in the stratigraphic record. If you suddenly see more fine sediment in ocean basins, or a shift in grain size, or an abrupt change in deposition rates, that is a signal. It doesn't tell you the cause by itself, but it narrows the story. A fourth bucket is biological consequences. This is an indirect route, but it's powerful. If a species altered the environment at large scale, other species would respond. You might see extinction patterns, shifts in pollen, changes in microfossil assemblages in ocean sediments, sudden invasions of species into new regions, or signs of widespread habitat disruption. Biology is a sensitive instrument. It reacts. And those reactions can leave traces in the fossil record. If you're noticing that all of these buckets are indirect, you're exactly right. Deep time proof tends to be indirect. It's evidence that something happened, not a photograph of what happened. Now, here's the part that often surprises people. Some of the most durable kinds of evidence might be things we don't instinctively think of as durable, because they're not objects at all. Take the idea of a boundary layer. In geology, there are moments where a sharp transition is recorded. A thin band of clay, a shift in fossil types, a change in chemical ratios. Some of these boundaries mark major events. If a hypothetical technological species had an industrial phase that was intense but short in geologic terms, it might leave a boundary-like signature, a narrow interval with unusual chemistry, perhaps accompanied by rapid ecological change. That kind of signature could persist for millions of years because it becomes part of rock. Even if continents move, even if landscapes erode, the layer may survive in some basins, preserved like a thin page in the planet's archive. But there are two problems. The first is that Earth's archive is incomplete. Many layers are lost, many rocks are recycled. The second is that we would have to distinguish an industrial boundary from other rapid events that also leave boundary signatures. So, what would make an industrial boundary distinctive? This is where people sometimes reach for very specific markers, like artificial radioactive isotopes, unusual synthetic compounds, or manufactured alloys. Radioactive isotopes are tempting because some have long half-lives. In principle, a nuclear civilization could leave detectable traces that persist for millions of years. But in practice, it's complicated. Many human-made radioactive materials decay relatively quickly in geological terms. Others can persist longer, but they can also be produced by natural processes in smaller amounts. And even if you could detect an unusual ratio, you would still need context. Where is it found? How widespread is it? What other signals accompany it? And are there plausible natural explanations? Synthetic compounds are another tempting idea. Plastics, for example, are unusual in nature. If plastics became buried and preserved, could they be detected far in the future? Maybe, but plastics degrade, fragment, and react. Over millions of years, it's not obvious they'd remain as recognizable polymers. They might leave behind carbon-rich residues or altered microstructures. In some settings, they could become incorporated into rock-like composites. But again, this would likely look like chemistry and microstructure, not like a shopping bag politely waiting to be discovered. Manufactured alloys sound promising too, because certain combinations of metals are uncommon in nature. But metals corrode. Alloys can separate. Elements migrate. A steel beam left to weather becomes rust, and rust becomes part of soil chemistry. Over a very long time, that chemistry could still be unusual in a layer, but it would not look like a beam. So you see the theme. The longer the time, the more the proof shifts away from obvious objects and towards subtle patterns that require careful interpretation. That leads to a very practical question. Where would these patterns survive best? Not everywhere. The planet does not preserve evenly. Ocean sediments can be excellent record keepers because they accumulate steadily in many places, especially in deep, quiet basins. Tiny shells of microorganisms rain down, dust settles, particles drift, and layers build slowly. Over long time, these layers can become rock and preserve detailed chemical and biological records. That's one reason deep-sea cores are so valuable for reconstructing climate and ocean history. But the ocean floor has a problem. Much of it gets recycled. So while sediments can keep a nice record, the record might only last until the crust beneath it is subducted. That puts a time limit on many deep-sea archives. Continental sedimentary basins can preserve very old sequences, especially in stable regions where rocks are not heated too much or crumpled beyond recognition. These basins can hold layered histories for tens or hundreds of millions of years. If you wanted long-term storage, you'd look to those. Caves can preserve things, but caves are tricky on deep time. A cave system can collapse, fill, or be dissolved away. Still, certain karst environments can preserve pockets of older sediments. It's not impossible, but it's not the main place you'd expect a multi-million-year record of surface objects. Polar ice is an excellent archive, but only for a limited window. Ice sheets don't typically persist unchanged for millions of years. They advance and retreat with climate cycles. So ice cores are wonderful for hundreds of thousands of years, but they're not a deep-time vault. Amber can preserve biological material remarkably well, but again it's selective. It's great at capturing small organisms and plant parts under certain conditions. It's not a typical container for industrial signatures, so the best long-term evidence would likely be in sedimentary rock sequences that have stayed relatively stable and readable. Even then, you have to think about what survives the conversion from sediment to rock. As sediments are buried, they compact. Water is squeezed out. Minerals precipitate. Chemistry shifts. This process can preserve some signals beautifully and blur others. A fossil shell can dissolve and leave only a mould. A delicate structure can flatten. A chemical signature can diffuse. What survives is often what is either abundant, widespread, or locked into stable minerals. So if a technological presence was small, localized, and short-lived, its signals might never rise above the noise of natural variation, not because nothing happened, but because the footprint was too light and too local, and the planet's filtering system erased it. This is another point where it's easy to drift into extremes. Some people hear that evidence is hard to preserve and conclude, then anything is possible. Others hear it and conclude, then we can never know anything. Neither is quite right. The more balanced view is that some kinds of activity would leave detectable signals and some would not. And the question becomes, how big, how long, and how widespread would a prior presence have to be for its signature to stand out in the record we still have? If you imagine a tiny society living quietly with low population and minimal material transformation, it could vanish almost without a trace. If you imagine something industrial on a global scale, altering the atmosphere and oceans significantly, it becomes much harder to hide from geology. Even then, you would still need the right rocks, the right preservation, and the right interpretive framework to notice it. So, the problem of proof is not a brick wall, it's a set of filters. The scale of activity, the kind of activity, the environment it occurred in, the preservation conditions, the survival of the archive, and our ability to interpret what we find. If you're still with me and not already drifting off, you can test the idea against something familiar. Think about our own era. What are the broad, planet-wide signals of modern humans? Rising greenhouse gases, a distinctive carbon isotope pattern from burning ancient carbon, widespread distribution of certain pollutants, large-scale land use changes, a sharp acceleration in extinction rates, global movement of species, new kinds of sediments influenced by construction and agriculture, and a layer of manufactured materials. Not all of these will last the same way, but some of them might leave a boundary-like signature. Now imagine those signals after millions of years of burial and alteration. The story wouldn't be, they had smartphones. It would be, something caused a rapid shift in carbon cycling, a wave of ecological disruption, and a spread of unusual materials. That's still a story, but it's a story told in a different language. And that language can be frustrating because it isn't dramatic in the way our minds like. We like clear objects. We like names and dates. We like a plaque next to the artifact. Geology offers none of that. Geology offers hints. There's also a subtle emotional challenge here that people don't always notice until they feel it. We want proof to feel satisfying. We want it to feel like closing a book with the answer in the last paragraph. Deep time evidence rarely provides that kind of satisfaction. It gives you probabilities and competing explanations. It gives you a set of interpretations that get stronger when multiple lines of evidence agree. So if you find yourself thinking, this is all too uncertain, that reaction makes sense. It's uncomfortable to live with uncertainty. But uncertainty is not the same as emptiness. It's a sign that the system is complex and the record is incomplete. Now, as you settle into this, it's worth noticing that the very difficulty of proof also protects us from jumping too quickly into belief. The bar is high, it has to be high, because natural processes can mimic many signals, and because humans are very talented at building exciting narratives out of partial information. A careful approach would look for combinations. A chemical anomaly plus an ecological anomaly plus an unusual distribution of certain elements, all aligned in time and found across multiple regions. It would look for patterns that are hard to generate through one-off natural events. It would compare what's seen with what models predict for known causes like volcanism or impacts. It would stay open to being wrong. In other words, it would look like normal good science, just applied to an unusual question. If you're listening from somewhere quiet, maybe your eyes are heavy now, and that's fine. The point to carry forward is simple. After millions of years, the most likely survivors are not monuments but signatures, thin, persistent fingerprints in rock and chemistry. And that naturally brings us to the next part of the conversation, because once you start thinking in terms of fingerprints, you start to notice something else. People have been pointing to strange hints for a long time. Not always good hints, not always reliable, sometimes just misread natural features, sometimes genuine anomalies that deserve a second look. If proof would have to come in the form of subtle signals, then it makes sense that the first clues anyone would talk about are the odd things that don't sit comfortably inside easy explanations. The little out-of-place marks and materials and stories that make someone pause and say, "That's interesting." There's a particular kind of moment that creates the feeling of a clue, and it doesn't require anything dramatic. It's the moment when something ordinary looking sits in the wrong context, and your brain quietly leans forward. A straight line where you expected a curve. A polished surface where everything else is rough. A concentration of metal in a place that doesn't seem to fit the surrounding rock. A story that appears in cultures that never met each other, told with different names but with a familiar shape. That moment is not proof of anything by itself, but it's how curiosity starts. It's the way you notice the kettle has stopped boiling. It's the way you notice your phone is missing when you're sure it was in your pocket. It's the soft internal tap that says, "Hold on, look again." When people talk about the strangest clues that something might have been here before us, they're usually talking about that feeling, stretched across geology and history. They're talking about the things that seem out of place, marks that look intentional, metals that seem concentrated in unlikely ways, myths that feel like memories. If you've spent any time online reading about mysteries of the ancient world, you've probably seen lists of these things. They're often presented as if one odd object changes everything, as if you can pick up a single stone or a single story, and suddenly the entire timeline of Earth flips over. In real science, it doesn't work like that. A good clue doesn't end the conversation, it begins a careful one. It asks a series of questions that are sometimes boring, sometimes technical, and almost always less dramatic than the headline. What is it made of? Where exactly was it found? How do we know its age? Could it have moved from somewhere else? Could natural processes produce something that looks like this? If it's a mark, what kind of tool would make it? And do we see consistent patterns? If it's metal, what geological processes concentrate that metal? If it's a myth, how does the story change across regions and time? Still, it's worth taking these strangest clues seriously in the one way they deserve, not as automatic evidence, but as prompts that force us to think about what would count as a signal in deep time, and what kinds of things can fool our eyes and our expectations. Let's start with marks, because marks are the easiest thing for a human mind to react to. We live in a world of marks made by intention. We're surrounded by cuts, grooves, letters, paint lines, tyre tracks, footprints, and construction seams. We know what purposeful marks look like because we make them constantly. Even when we're half asleep, we can tell the difference between a scratch made by a key and a crack made by stress in a material. Most of the time, our instincts are good. The trouble is that nature makes marks too, and it makes them on scales that are hard for our instincts to calibrate. Rocks crack along lines. Minerals form repeating patterns. Water cuts channels that can look like careful carving. Wind sculpts dunes into ridges that look engineered from above. Ice scratches bedrock in long, parallel grooves as it drags rocks underneath like rough sandpaper. Repeated waves can etch lines. Repeated falling stones can create smooth hollows. Chemical weathering can create honeycomb textures, grooves, and sharp boundaries between materials. Even the growth and shrinkage of clays can create polygon patterns that look like deliberate tiling. If you've ever seen dried mud broken into neat hexagons, you've already met one of nature's most convincing designed patterns. It's not designed, it's physics. And the older the world gets, the more physics has time to repeat itself. So when someone finds a line in rock and says that's a cut, the first response is not to laugh. The first response is to ask what kind of cut, and compared to what. Tool marks, when they're real, tend to have consistent features. They repeat. They show a direction. They show a pattern of force. They show microscopic striations that match a particular material. They appear alongside other signs of human or animal activity in the same layer. They don't sit alone like a single sentence ripped out of a book with no other pages. In the deep past, though, context is usually thin, and that's where the strongest mark-based mysteries live, in the space where the pattern looks intentional, but the surrounding evidence is missing or ambiguous. There are also large-scale marks, the kind you can see from the air, lines across a desert, shapes on a plateau, geometric arrangements that look like drawings. Some of these are absolutely human-made, like geoglyphs and earthworks, but those are within the known human timeline. The more speculative claims point to older, more eroded features and suggest they're remnants of ancient planning or construction. Here's the gentle problem. Landscapes produce geometry. Not all geometry, and not always cleanly, but enough to tempt the eye. Fault lines can create long, straight features. Fracture networks in rock can look like grid patterns. Drainage systems can create branching shapes that resemble design. And if you're looking at a satellite view with the thought already in your mind, if you're hoping to see intention, you'll see intention more easily. That's not an insult to anyone. It's how perception works. The brain is a pattern engine. It's always doing its best with incomplete data. In a way, the strangest clues are often clues to that fact. We're not just studying Earth, we're studying what a human mind does when it stares at Earth for too long. Now, metals. Metals have a special power in these discussions because they feel like technology. When you see a concentrated mass of metal, you don't think wind and rain. You think smelting or manufacturing or mining. You imagine hands and tools and deliberate extraction. That reaction is understandable, because in our experience metals in pure or concentrated form are often associated with human activity. But Earth is a chemist, and it's been doing chemistry longer than anything else we know. It concentrates metals through processes that don't require mines. Hydrothermal systems, for example, can move metal-rich fluids through rock and deposit veins of ore as temperatures and pressures change. That's how you get concentrated gold, copper, lead, zinc, and other metals in specific geological settings. Volcanic activity can concentrate metals too, both through lava chemistry and through the hot fluids that circulate around magma. Sediments can concentrate heavy minerals by sorting them, the way waves sort sand grains. Iron can be laid down in huge quantities under certain ancient ocean conditions. Manganese can form nodules on the seafloor, slowly building up layers around a nucleus like a pearl, except the pearl is made of metal oxides. So if you find metal in a place that surprises you, the first step is to ask, does geology have a pathway for that? Often, it does. Still, there are a few types of metal clues that keep showing up in popular discussions because they feel particularly unsettling. One is the idea of refined or processed metal, appearing in very old contexts. People sometimes claim to have found an object made of metal alloys in rock layers that are far older than humans, and they present it as decisive evidence that someone must have made it long ago. In many cases, when these claims are investigated, the object turns out to be modern debris that got embedded in a concretion or misinterpreted geological formation. Concretions are one of the planet's quiet tricks. Minerals can precipitate around an object and harden into a rock-like mass, giving the impression that the object was inside ancient stone when it was actually enclosed relatively recently. If you've ever seen a rusty nail encased in a hard lump and thought it looked ancient, you've seen the basic mechanism. Another recurring claim involves objects found in mining operations. Someone drills, something odd comes up, and the story spreads. An impossibly old artifact was pulled from deep underground. The difficulty is that mines are messy environments for storytelling. Material falls in from above, equipment breaks, debris moves, samples get mixed. Without careful documentation, chain of custody, and reproducible analysis, a dramatic claim can be nothing more than a mix-up wrapped in excitement. This is why the scientific response to metal-based anomalies tends to be slow and procedural. If you truly had a manufactured alloy embedded in a securely dated rock layer millions of years old, it would be extraordinary. It would also be testable in a very straightforward way. Analyze the alloy, examine the microstructure, look for manufacturing signatures, date the surrounding materials with multiple independent methods, and see if the context holds up under scrutiny. The key is that extraordinary evidence doesn't come from one person's story. It comes from a chain of measurements other people can repeat. If you feel a small sigh in your chest when you hear that, you're not alone. Many people want mysteries to remain mysteries. They want a single object to be enough. Science asks you to keep the object and also keep the paperwork. Now, there is a more subtle kind of metal clue that is actually aligned with how deep time evidence would realistically survive. Not a single artifact, but a chemical anomaly in sediments. A spike in certain elements across a layer. An unusual ratio of isotopes. A distribution pattern that doesn't match typical natural events. These are the sorts of things Earth can preserve as fingerprints. But here the planet plays another trick. Some of the strongest natural events also leave metal anomalies. Meteor impacts can deposit iridium and other elements in ways that stand out, because meteorites have different compositions than Earth's crust. Large volcanic events can spread ash and aerosols that alter chemical signatures. Ocean anoxia events can concentrate certain metals in sediments, because oxygen levels control how metals dissolve and precipitate. So you can't see a metal spike and immediately point to industry. You have to compare it to known natural fingerprints, and you have to look for combinations of signals rather than a single one. If you've ever watched a detective show and rolled your eyes because the detective solves the case from one hair on a jacket, geology is almost the opposite. Geology solves the case by looking at several boring hairs, some dust, a footprint that might be a footprint, and a slight change in temperature, and then saying, we can't be certain, But here's what's most consistent. So marks can be misleading, metals can be misleading, and that brings us to myths, which are the most human kind of clue in this whole conversation. Myths are often treated in two extreme ways. Some people dismiss them entirely, as if a story told by humans can never contain any trace of real events. Other people treat myths as literal records that only need decoding, as if every legend is a historical document wearing a costume. Both extremes miss what myths actually are. Myths are stories that travel. They carry values, warnings, identity, and memory. They change with retelling. They absorb local details. They get shaped by language and politics and religion. And sometimes, embedded in all of that, they can preserve a shadow of real experiences: floods, droughts, migrations, eruptions, strange lights in the sky, the slow rise of the sea. If you look across cultures, you will find recurring story shapes: great floods, lost golden ages, divine punishments, civilizations that fell because of pride or violence, teachers who came from far away and taught people to build, islands that sank, lands that were swallowed by the ocean, fire from the sky, long winters. These motifs are common enough that people sometimes treat them as a global memory of a single ancient event, or as evidence that advanced knowledge existed long ago and was later forgotten. A calmer approach is to notice that humans have lived through many similar kinds of disasters, and humans also share similar psychological needs. Coastal communities see the sea rise and storms erase shorelines. River communities see floods wipe out settlements. Volcanic regions experience eruptions that feel like the world ending. Ice ages end and sea levels rise dramatically over long periods, swallowing land that used to be habitable. When people survive these things, they tell stories. Over generations, those stories can grow into myths. So when you hear a flood myth, the grounded question is not, is this Atlantis? It's what local events could have inspired this story, and how does the story map onto what we know about regional geology and climate? Sometimes the answer is surprisingly specific. Sometimes it's general. Sometimes it's impossible to pin down. But it's not nothing. Myths can also preserve a sense of time that isn't measured in years, but in before and after. Before the flood, after the flood, before the fire, after the fire, before the sea took the land, after we moved inland. That before and after can align with real transitions, even if the details don't. Now, here's the part that connects myths to our broader theme in a way that doesn't require any wishful thinking. Even if myths are not literal records of ancient technology, they show that humans are very sensitive to the fragility of civilizations. People have always known that settlements can vanish. People have always known that the ground is not guaranteed. That knowledge gets encoded into stories because it's important. It's a survival lesson. So when modern people imagine something before us, they're also tapping into an old human habit, looking backward for lost worlds, partly out of curiosity and partly out of anxiety. We sense, even if we don't say it, that our own world is not permanent. Myths are one way humans have always processed that feeling, and there's a gentle irony here. If an earlier presence existed long before modern humans, it might not have left myths for us at all. Myths require continuity. They require a chain of storytellers. They require memory passed down through language. Deep time tends to break chains. Species go extinct. Languages vanish. Continents rearrange. A prior presence might leave chemistry, not stories. So myths are not a direct pipeline to deep time truth, but they can help us understand why this question keeps returning. They show that the idea of lost worlds is not a modern internet invention. It's part of how humans relate to Earth. Now, there is a kind of clue that sits between myth and measurement, and it's the category of things that are real but commonly misused, genuine anomalies that science hasn't fully explained yet, or that took a long time to explain. These are important because they teach humility without demanding belief in anything specific. In geology and archaeology, there are plenty of cases where something looked wrong at first, because the prevailing story was incomplete. Strange layers that didn't fit the expected climate, fossils found in places they shouldn't be, evidence of human presence earlier than accepted timelines. These cases don't prove an earlier civilization in deep time, but they do show that the record can surprise us and that confidence can be temporary. At the same time, there are also plenty of cases where strange clues turned out to be ordinary once the context was understood. A groove was a glacial scratch. A carved stone was a natural fracture. A metal object in ancient rock was a modern item in a concretion. A map was misread. A date was misassigned. A story was exaggerated. So the reality is mixed, and that mixed reality is exactly what makes the strangest clues so sticky. There's enough genuine surprise in the world to keep the imagination alive, and enough error and exaggeration to keep scientists cautious. If you're still awake enough to notice your own mental posture, you might feel the tug in two directions. One tug says, maybe there's something here. The other tug says, be careful, humans love to jump. The most useful position is somewhere in the middle, curious but disciplined. One way to keep that discipline is to ask a simple question whenever you encounter an out-of-place mark or metal or myth. What would have to be true for this to be strong evidence? And do we have those things? Do we have secure dating? Do we have multiple independent lines of evidence? Do we have replication? Do we have a plausible mechanism? Do we have context that rules out simpler explanations like natural processes or recent contamination? If the answer is no, you can still enjoy the mystery, but you don't have to treat it as a conclusion. Another way to stay grounded is to remember that deep time evidence is more likely to be widespread than singular. One perfect artifact is the kind of thing a story loves. A thin chemical fingerprint across multiple basins is the kind of thing geology is more likely to provide. The planet is better at preserving patterns than preserving sculptures. And there's a final point about strange clues that matters for the larger question we're exploring. Even if every popular out-of-place artifact story turned out to be wrong, and even if every myth was just myth, the underlying thought experiment would remain. Earth can erase surface civilizations. The record is incomplete. The best evidence would be indirect. That means the hunt for clues should eventually shift away from internet lists and toward the kinds of signals Earth reliably stores: isotopes, sedimentation changes, persistent pollutants, extinction patterns, and long-lived geochemical anomalies. If you like this kind of slow, careful unravelling of strange topics, you can subscribe to Just About Earth. It's the quiet kind of support that makes more of these possible, and you don't have to do anything else beyond that. As you settle further into wherever you are, consider how the word clue changes shape depending on the timescale. In a human crime story, a clue is a fingerprint on glass. In deep time, a clue is often a faint change in the chemistry of a layer, a subtle pattern that only looks meaningful when you compare many samples and see the same signal repeating. So the out-of-place marks and metals and myths are not a final answer. They're more like training exercises. They teach you what can fool you, what can genuinely surprise you, and what kinds of questions matter if you want to talk about earlier presences without drifting into fantasy. And once you start thinking that way, the next thought appears almost automatically, because you begin to wonder what kind of earlier presence would even be capable of leaving a recognizable signal at all. Not a hidden human empire, not a lost city behind a waterfall, but a different kind of intelligence with a different relationship to the planet, living long enough to matter, and then disappearing into the same processes that erase everything else, leaving behind only a faint trace that we might finally be learning how to notice. When people imagine someone before us, they almost automatically imagine someone like us. 2 arms, 2 legs, hands that can hold tools, eyes that focus forward, a voice that tells stories. It's understandable. We're using our own minds to picture another mind, and our own bodies to picture another body. It's hard to do anything else without drifting into cartoons. But if you take the question seriously, even as a thought experiment, it immediately asks you to loosen that grip. Because Earth has hosted life in more forms than our instincts are prepared for, and intelligence is not a single mould that every world must pour itself into. If anything was building before modern humans, it doesn't have to fit the silhouette we're used to. You might be listening and thinking, all right, but what do you mean by intelligence here? That's a fair question, because the word gets used loosely. Sometimes people mean brain size. Sometimes they mean language. Sometimes they mean technology. Sometimes they mean a species that can do math and build machines. Those are related, but they aren't the same. A calmer way to approach it is to treat intelligence as a set of abilities that can exist in different combinations. The ability to learn, the ability to solve problems, the ability to communicate complex information, the ability to plan, the ability to cooperate, the ability to reshape surroundings intentionally. Humans are one particular bundle of these abilities. We didn't just become clever in isolation. We became clever in a way that stacks and spreads. Our knowledge accumulates. It gets passed on. It scales from a small group to a huge society. That scaling is what makes our impact so large. So when we ask whether another kind of intelligence could have lived here, we're really asking two questions at once. First, could another species have developed high-level cognition and social complexity long before us? Second, could it have developed behaviours that leave durable traces in the environment, the sort of traces that could still be detectable after millions of years? Those two questions are not identical. You could have intelligence without large-scale environmental change. You could have environmental change without what we'd call high intelligence. And you could have a lot of intelligence that is simply invisible to geology, because it doesn't rely on the kinds of materials or processes that create long-lived signatures. If you're getting comfortable as you listen, you don't need to chase every branch of this. Just keep the central idea. We are not the only kind of mind the planet can produce, and we're not the only way a mind could interact with the world. One reason this topic feels strange is that we tend to treat our own rise as the obvious destination of evolution. It's easy to look at the world and think, of course, intelligence like ours was bound to happen eventually. But evolution doesn't work like a conveyor belt that moves toward a goal. It's more like a series of experiments shaped by environment, chance, and survival pressure. Sometimes complexity increases, sometimes it doesn't. Sometimes the same general capability evolves independently in different lineages because it's useful, and sometimes it never appears because the conditions don't favour it. Even on modern Earth, you can see different kinds of intelligence expressed in different ways. Some animals solve puzzles, some use tools, some have complex social dynamics, some show long memory and learning, some can understand cause and effect, some can cooperate in coordinated groups. These aren't just cute anecdotes. They are evidence that advanced cognition is not exclusive to one lineage. It can show up wherever the ecological and biological conditions support it. But the leap from smart animal to builder of lasting structures is not automatic. And this is where you can start to see why humans might be unusual in a very specific way. A mind can be capable without having the right body or environment to turn capability into durable impact. Hands matter. Fine motor control matters. The ability to manipulate objects repeatedly and precisely matters. Humans have hands that can make a wide range of grips, and that makes toolmaking easier to develop and refine. But hands are not the only way. Some animals use beaks, some use mouths, some use tentacles, some use claws. The question is whether those body parts can support repeated manufacturing behaviours, and whether those behaviours can become culturally stable enough to accumulate across generations. Fire matters too, not because it's magical, but because it's a gateway. Fire allows cooking, which can change diet and energy availability. Fire allows heat treatment of materials. Fire allows the reshaping of environments through controlled burns. Fire is also a stepping stone to metallurgy and to other high-energy processes. If a lineage never gets a stable relationship with fire, its technological pathway might be very different. That doesn't mean it can't become intelligent. It means its signature might not look like ours. Environment matters in the same way. A species living mostly in the ocean might develop complex cognition, but the ocean is a difficult place for certain kinds of technology. Fire is hard underwater, metals corrode, structures are battered by currents. Building on the seafloor is possible in principle, but the materials and methods would differ. And even if such a species built something, the preservation story might not favour it in the long term, because much of the ocean floor is constantly recycled and reshaped. So if you're imagining a prior intelligence, you have to picture not only a mind, but a set of constraints and opportunities. That sounds like it makes the idea less exciting, but it actually makes it more realistic. The most interesting possibilities tend to be the ones that feel slightly inconvenient, because reality is often inconvenient. There's another reason the question is tricky. The fossil record is not designed to show you minds. Fossils show you bodies, teeth, bones, shells, impressions, traces. You don't fossilize a thought. You infer cognition from anatomy and behaviour is mostly invisible unless it leaves physical traces like tool marks, nests, or patterns in bones. So if a highly intelligent species existed long before humans, we would likely not have a clean label for it, unless it left behind evidence that looks like deliberate manipulation of the environment. Without that, it could simply be another extinct lineage in the record, known by fragments of skeleton and little else. That might sound like it makes the whole idea impossible to evaluate, but it doesn't. It just changes what we should look for. We would look for indirect signs, anatomical features consistent with high manipulation ability, signs of long childhood and learning, evidence of complex social living, and most importantly, traces of behaviour that go beyond ordinary animal activity. And here, it's important to be honest about what we already know. We don't have evidence of a pre-human industrial civilization in the deep past. If we did, it wouldn't be a quiet niche topic. It would reshape multiple fields. The standard scientific view is that no such evidence has been found. That's the current state. But our larger question is not, is there proof right now? It's, is it possible in principle? And if so, what would the evidence look like and why might it be missing? To keep this grounded, it helps to ask what kinds of non-human builders exist today, because builders don't begin with factories. They begin with simple construction that becomes more elaborate over time. Beavers build dams that reshape waterways. Termites build mounds with ventilation systems. Ants create massive underground networks. Corals build reefs that become whole ecosystems. Birds build nests, sometimes with impressive architecture. Octopuses arrange stones and shells for shelter. None of these animals are civilized in the human sense, but they show that the urge and ability to modify an environment is widespread. Now imagine these behaviours amplified over longer time and different conditions, not necessarily amplified into skyscrapers, but amplified into large-scale landscape effects. A species doesn't have to invent writing or metalworking to qualify as a significant builder in geological terms. It might only need to consistently move sediment, redirect water, concentrate certain materials, or alter ecosystems in a persistent way. If you're listening and you're thinking, that sounds like it could blur into normal ecology, you're right. That's part of the challenge. Many non-human species alter landscapes. In fact, life as a whole has been altering Earth's chemistry and surface for billions of years. Plants changed the atmosphere, microbes changed oceans, the spread of forests changed erosion patterns. Life is a geological force, so the question becomes, could a specific lineage with higher cognition and more deliberate behaviour create a distinctive footprint within the broader footprint of life? One way to approach that is to focus on scale and concentration. Natural ecosystems create patterns, but they often distribute effects across many species and many processes. A technological species Even a modest one tends to concentrate its effect through focused extraction and manufacturing. It takes materials that are dispersed and gathers them. It takes energy flows and channels them. It creates new combinations. It does this in a way that can leave sharper signatures than a diffuse biological background. But there's a catch that matters a lot if we're imagining an earlier intelligence. Our own industrial footprint is partly a result of our particular history and our particular energy sources. We had easy-to-access fossil fuels in the ground. We had large forests and fertile soils. We had a climate and geography that allowed agriculture to scale. We developed metallurgy and then machines. We built on top of earlier steps. A different lineage might not follow the same route. It might never access fossil fuels. It might never reach metallurgy. It might develop a complex culture that's mostly biological or chemical rather than mechanical. It might use living materials. It might build with stone and wood and plant-based composites. It might modify ecosystems rather than making machines. If that sounds vague, imagine a species that becomes extremely skilled at cultivating and shaping living systems, the way humans have with agriculture, but far more deeply integrated. Think of it as an ecology-based technology rather than an industrial one. It could still have profound effects, but the physical artifacts might be minimal. Its infrastructure might be living networks, not metal frameworks. Over millions of years, that could leave almost nothing recognizable as a deliberate system, because living systems decay and merge back into the background. So it's possible that an earlier intelligence could exist and still be almost archaeologically invisible, especially if it never crossed certain thresholds of material transformation that create persistent non-biological residues. At this point, it's worth asking a very plain question. If another intelligent lineage existed, why didn't it survive to the present? That question doesn't require any special answer. Extinction is common. The planet has seen multiple mass extinctions and countless smaller ones. Whole groups disappear. Sometimes they disappear because of sudden disasters like impacts or massive volcanism. Sometimes they disappear because of slow climate shifts. Sometimes they disappear because of ecological competition. Sometimes a small change in the world is enough to wipe out a specialized lineage. Even humans, who feel so dominant now, are not protected from the basic vulnerabilities of biology. We have technology, but we still depend on food, water, stable ecosystems, and a climate with intolerable ranges. We're not separate from the system. We're a part of it, just a part with a lot of tools. So an earlier intelligence, if it existed, could have disappeared for the same reasons anything disappears. And if it disappeared long ago, Earth would have had ample time to erase most obvious traces. Another possibility is that an earlier intelligence might not have been widespread. It might have been geographically limited, living in one region, or in a set of island chains, or along a now-vanished coastline. If its population was small and its footprint local, its chances of leaving a global geochemical signature would be low, and its chances of leaving durable artifacts would depend heavily on whether the region where it lived became a good preservation environment. This matters because we tend to picture civilizations as large and sprawling because ours is. But there's no rule that says intelligence must scale into global reach. It might remain local for long periods, especially if the ecological niche it occupies is stable and the incentives to expand are weak. So when we talk about forgotten builders, it may be more accurate to picture a spectrum. On one end, a highly intelligent species that builds mostly with living systems and leaves almost no durable trace. In the middle, a species that modifies landscapes and creates structures that erode into ambiguous patterns. On the far end, a species that becomes industrial and leaves chemical fingerprints that could stand out if preserved. Each point on that spectrum has different implications for what we could detect. If you're feeling your mind drift toward the ocean again, that's natural, because the ocean is both a plausible home for complex intelligence and a place that feels hidden. Dolphins and whales show social complexity and communication. Octopuses show problem solving. The ocean feels like a world we still don't fully know. But it's worth remembering that an ocean-based technological path has real constraints. Even if a species became extremely intelligent, building durable industrial systems underwater is hard, and preserving evidence on the ocean floor is uncertain because much of it is geologically young. Meanwhile, land-based intelligent species have different constraints. Land is better for fire. It's easier to build stable structures. It's easier to manipulate materials without constant corrosion. But land also experiences its own erasures through erosion, burial and tectonics. So neither environment is a perfect vault. Both are active. There's also an important psychological temptation here, to treat unknown intelligence as automatically superior. People sometimes assume that if something existed before us and vanished, it must have been more advanced, more enlightened, or more powerful. That assumption comes from story logic, not from biology. In the real world, being advanced doesn't guarantee survival. Sometimes specialization is fragile. Sometimes complexity adds vulnerabilities. Sometimes being too dependent on a particular resource becomes a trap when conditions change. So a prior intelligence, if it existed, could have been impressive in some ways and limited in others. It could have been clever without being industrial. It could have been social without being expansive. It could have been skilled in one domain and vulnerable in another. And there's another quiet thought that tends to follow. If a prior intelligence existed and disappeared, could we be missing it in the fossil record because we haven't looked for the right signs? That's not an accusation against science. It's a reminder that science is shaped by questions. If you don't ask a particular kind of question, you may not design your studies to detect the answer. Paleontology has historically focused on bodies and evolution. Geology has focused on rocks and processes. Archaeology has focused on humans and recent prehistory. The idea of searching for non-human technological traces in deep time sits awkwardly between fields. It requires combining methods and, more importantly, deciding that it's worth asking. That decision is part of what makes this topic feel like it's only now being considered. It's not that no one ever had the thought, it's that the tools and frameworks to explore it seriously have only recently become available, and even now it remains a niche question because the evidence is expected to be subtle, and the risk of misinterpretation is high. If you're listening from a place where sleep is close, you might notice the tension easing a little when you frame it that way. It becomes less like a conspiracy and more like a practical research problem. What signals would survive, and how do you distinguish them from natural patterns? One gentle way to keep your footing is to ask what would count as a builder in geological terms. Humans build with concrete and steel, but those are just materials. The deeper idea is organization, repeated, deliberate transformation of the environment. If another kind of intelligence existed, its building might not be towers. It might be chemical processing using biological methods. It might be long-term shaping of watersheds. It might be controlled breeding and moving of species. It might be large-scale modification of soils. And this is where the topic starts to point towards something that can sound almost counterintuitive. The most durable sign of an earlier builder might not be a structure at all. It might be the absence or rearrangement of something natural. A sudden shift in species distributions that doesn't match climate alone. A persistent, unusual pattern in sediments that suggests altered erosion. A chemical signal that indicates concentrated processing. In other words, the traces might be the kind that you only notice once you stop expecting cities. That thought is a useful bridge, because it sets up the next step in our exploration. If we let go of the idea that prior intelligence would leave behind obvious ruins, we can start to think about what infrastructure would look like in deep time, and how a civilization might exist in a way that is archaeologically quiet, leaving behind patterns rather than monuments. So as you rest where you are, and as the world outside your room, or your car, or your late-night kitchen keeps turning without asking anything from you, let the idea settle gently. Another kind of intelligence is not impossible in principle. but its footprint might not be what our imagination keeps reaching for, and that changes where we look and what we consider to be a meaningful trace. When you hear the word infrastructure, you probably picture things that are obvious even from a distance. Roads cutting through a landscape, bridges spanning water, trains sliding along rails, power lines strung across pylons, ports, tunnels, pipelines, airports, and those clusters of buildings that from far away look like a solid block of human intention. The word carries a certain weight because it implies permanence. Infrastructure is what people build when they expect to stay. Now take a slow breath and imagine trying to explain that same idea to someone who arrives on Earth 10 million years from now. Not 10,000, not 100,000, but 10 million. The question isn't whether they would find a city standing there, because they almost certainly wouldn't. The better question is what infrastructure becomes after the planet has had enough time to chew on it, bury it, remix it, and in many places recycle it entirely. What does a road look like after it has been ground into sediment, pressed into rock, heated and altered? What does a port become when sea levels change, coastlines migrate, and the seafloor itself is replaced? This is the key shift for tonight. In deep time, infrastructure stops being a set of visible objects and becomes a set of patterns. It becomes disturbances in layers, unusual concentrations, odd mixes of materials, and changes in how landscapes behave. In other words, it becomes the kind of evidence Earth is actually good at storing. If you're listening from somewhere quiet, you can let that settle without forcing it. And if you're listening from a place where there's a little noise in the background, that's fine too. Earth is noisy. The record it keeps is still there. A helpful way to ground this is to notice that even today, we already recognize older human infrastructure mostly through indirect signs. An ancient road isn't always a clean strip you can walk on. Sometimes it's a subtle ridge in a field. Sometimes it's a line where the soil compacts differently. Sometimes it's a pattern in vegetation because moisture behaves differently over buried stone. Sometimes it's a faint straightness that doesn't match the rest of the landscape. The road is gone as an object, but the landscape still remembers it in how it drains, how it erodes, and how it grows. Deep time is that principle turned up to an extreme. So what might cities without cities look like when you strip away the skyline and keep only what survives the planet's long editing process? Start with the simplest idea. A city is not just buildings. A city is a concentrated arrangement of materials pulled from many places and gathered into one area. Stone from quarries, sand from rivers, metals from ore deposits, wood from forests, and a long list of chemical products made by transforming raw materials. Even if the buildings collapse and the shapes disappear, the concentration doesn't instantly vanish. It begins to spread out to mix with surrounding sediments and to react chemically, but the initial fact remains. Someone took a diffuse world and made it locally dense. That local density is one of the most basic ingredients of a long-lived signal. Geology likes bulk. It likes things that are common enough to show up in layers. A single sculpture is fragile. A whole region enriched in certain materials is more durable as evidence because it's harder to erase completely. Now, picture what happens to that dense mixture over time. Water moves through it. Oxygen reacts with exposed metals. Concrete breaks down and can become chemically similar to natural carbonate-rich rocks in some conditions. Glass shatters and becomes tiny fragments that can be rounded and incorporated into sediment. Plastics fragment and oxidize and may leave residues that are not recognizable as plastic objects, but could still alter the organic chemistry of a layer. Bricks and ceramics break into grains that don't behave exactly like natural sand. Asphalt breaks down, but its carbon content can still end up in soil and sediment as altered organic material. None of this requires a dramatic event. It's what happens when you leave a complex pile of stuff outside for long enough. The main difference in deep time is that the pile doesn't just sit there, it gets buried. And burial is both a form of hiding and a form of preservation. burial tends to preserve signals that are spread across a layer. Think of it like pressing a messy mixture into a sandwich and then sealing the sandwich in plastic wrap. The crumbs and sauces may smear, but the fact that there is a distinct layer of mess between two cleaner slices remains. In geology, that can show up as an interval with unusual mineral fragments, unusual chemical ratios, or an odd mix of particles that doesn't match what you'd expect from ordinary erosion. If you want a concrete example without getting too technical, imagine the difference between a natural beach sand and a sand made from crushed buildings. Natural sand often has a particular mix of quartz and other minerals depending on where it came from. Crushed building debris can add large amounts of cement minerals, brick fragments, glass shards, and metal oxides. Over time, those components can change, but the mixture can still be distinct from ordinary river sand, especially if it is widespread enough and deposited in a basin where layers accumulate steadily. So one possible form of infrastructure in deep time is a thin, laterally extensive layer that contains a strange mix of materials that normally don't appear together in that proportion. Now shift from cities to the networks that feed them, because this is where infrastructure becomes less like a photograph and more like a system. A city depends on roads and rails, on pipelines, on power generation, on agriculture, on mining, and on waste removal. These networks spread outward, and their footprints can be larger than the city itself. Roads, for example, are not just lines on a map. They are engineered surfaces that change how water flows. They compact soil. They create cut slopes and fill slopes. They redirect drainage into culverts and ditches. They can trigger erosion by concentrating runoff. Even when the road surface is gone, the reshaped topography can influence how a hillside erodes or how a valley fills. Over long time, a road is likely to vanish as an object, but the sediment it triggered might not vanish. A period of intense road building across a region could increase sediment delivery to rivers, which increases sediment delivery to deltas and coastal shelves, which changes the thickness and grain sizes of layers laid down offshore. So in deep time, one signature of infrastructure might be not a preserved road, but a change in sedimentation rates and patterns that coincides with large-scale landscape disturbance. Agriculture and land clearing do something similar. When you remove forests and disturb soil, erosion rates can rise. Rivers carry more sediment. Floodplains build up faster. Deltas grow and shift. Lakes fill with silt. Those processes leave very readable signals in sediment layers, and they can happen quickly compared to geologic background rates. Again, nature can also cause shifts like this, so the signal isn't automatic proof of anything, but it's the kind of pattern you can measure and compare across regions. Mining is another strong candidate for long-lived signatures because it involves concentrating and redistributing elements. If a species mined copper, lead, gold, lithium, or rare earth elements on a large scale, it would move those materials from deep rock into surface systems. Smelting and refining can release metals into air and water. Tailings can spread into river systems. In modern times, you can see heavy metal signatures in lake sediments near industrial areas. Over millions of years, those metals can migrate and react, but they can also become locked into minerals or remain as elevated background levels in certain layers, especially in basins where fine sediments accumulate. If you're thinking, but our deposits exist naturally, you're right, and that's why context matters. A natural ore body tends to be localized and tied to specific geological structures. An industrial footprint tends to spread metals into places they wouldn't otherwise concentrate, like widespread thin layers in lakes and seas, or consistent elevation of certain elements across a broad region that doesn't match known mineralization patterns. It's the difference between a single, naturally rich vein and a faint, widespread haze from processing and dispersal. Now consider energy, because infrastructure is really a way of managing energy. You can't run a large society without moving energy from where it is available to where it is used. In our world, that includes extracting fossil fuels, building grids, and producing huge amounts of heat and electricity. In a deep time record, the electrical grid itself won't survive. Wires corrode, towers fall, the shapes disappear. But the byproducts of energy use can be durable, especially when energy use becomes large enough to alter the chemistry of air and water. Combustion, in particular, has a footprint. Burn enough carbon, and you can shift the balance of carbon isotopes in the atmosphere and oceans. Produce enough soot, and you can leave black carbon in sediments. Create enough industrial nitrogen compounds, and you can leave changes in nitrogen cycling that show up in sediments and fossil assemblages. A large, fast release of greenhouse gases can trigger warming that changes ocean chemistry, which affects the shells of microorganisms that later become microfossils. Those microfossils accumulate in layers and preserve a climate story that can last for millions of years. None of this requires you to imagine towering cities lasting intact. It requires only that a large-scale system ran for long enough to leave a measurable change, and that the change was captured in a basin that preserved layers. That's a theme worth repeating gently, because it's the backbone of this whole cities without cities idea. Deep time is not kind to objects, but it is sometimes kind to signals. If you want to make it slightly more personal, you can run a thought experiment with a place you know. Pick a city you've been to, or even just the town where you live. Imagine it empty, then imagine it after 1,000 years, then after 100,000. By the time you reach 1,000,000 years, most recognizable structures are gone. The question becomes what survives in the ground and in nearby sediments. There might be a layer rich in certain kinds of particles. There might be altered soil chemistry over what used to be landfills. There might be unusual erosion patterns recorded downstream. There might be a boundary in a lake sediment core that marks a period of rapid change in land use. Landfills are worth dwelling on for a moment, because they're a kind of infrastructure that people don't like to talk about. They're also a kind of infrastructure that geology is very good at turning into a layer. A landfill is a concentrated deposit of mixed materials, often covered and then left. Over time, it can be buried deeper by later sediments, and its contents can be altered, but the site can remain chemically unusual for a very long time. Even if plastics and organics break down, they can leave behind a concentrated carbon signature, unusual metal distributions, and mineral changes in surrounding sediments. If a future geologist found a thin seam with elevated concentrations of certain elements, odd fragments, and an unusual organic chemistry, they might not call it trash. They might call it an anomalous deposit. If they found many such deposits clustered in a region and aligned in time, they might infer a behaviour, something systematically concentrated and buried mixed materials. That's what infrastructure looks like when translated into the language of strata, behaviour inferred from repeated patterns. Now, here's where the phrase cities without cities becomes more than just a catchy idea. It forces you to admit that infrastructure does not have to be hard, metallic, and obvious. It can be biological, it can be chemical, it can be distributed, it can be temporary in the way a beaver dam is temporary, yet still influential in how a valley develops. It can be a network of altered ecosystems that leaves behind a different fossil and pollen record. It can be a long-term reshaping of a watershed that changes sediment loads for hundreds of thousands of years. If another kind of intelligence existed, and if it built systems that relied heavily on living materials, its infrastructure might leave a lighter direct footprint, but still leave indirect signatures in how ecosystems changed. For example, if a species moved organisms around deliberately, you might see sudden appearances of certain species in places that don't match climate changes. If it practiced widespread cultivation, you might see pollen records dominated by certain plants, in a way that looks like selection rather than natural spread. If it altered soils consistently, you might see unusual soil horizons or chemical changes in sediments downstream. This is not meant to suggest that every strange pollen record is evidence of a forgotten builder. It's meant to show how the very definition of infrastructure changes when you stop thinking in terms of steel and start thinking in terms of system-wide effects. You might notice that this way of thinking also reduces the urge to look for one dramatic relic. It shifts attention toward things that are measurable. You can take a core sample and measure isotopes. You can map element concentrations. You can compare sedimentation rates across regions. You can model whether a given pattern is more consistent with natural events or with sustained disturbance. It becomes less like hunting for a lost city, and more like reading a long set of records for unusual changes. There's a quiet satisfaction in that, even if it's not flashy. It makes the problem feel less like a story and more like a research question. Now let's deal with the frustration that naturally pops up here. If infrastructure in deep time becomes subtle patterns, then couldn't those patterns always be explained by natural processes? Doesn't that make the whole exercise impossible? It makes it difficult, but not impossible. Difficulty is not the same as hopelessness. Scientists distinguish between causes all the time using patterns. An impact leaves different signatures than volcanism. A rapid climate warming event driven by one mechanism looks different in detail than one driven by another. Ocean anoxia events have characteristic markers. Even if multiple causes can produce similar broad outcomes, the combination of markers can help narrow the story. If a hypothetical prior infrastructure left a signal, the strongest case would come from multiple lines of evidence pointing in the same direction. Unusual chemical markers alongside rapid ecological disruption, alongside sedimentation changes, all tightly aligned in time and seen in multiple basins. It would not come from one strange rock, and if you're thinking, that's a high bar, it is. It should be. A high bar protects us from confusing interesting natural events with intelligent activity. This is also a good moment to check in with the feeling side of it. If you've been carrying this idea as a kind of thrill, you might notice it getting less dramatic as it becomes more technical. That's normal. The mind likes clear mysteries. The planet offers messy evidence. But there's another kind of wonder here, a quieter one. The realization that the Earth keeps records at all, and that with enough care you can read them. If you're settling into sleep, you can let that be the main takeaway from this stretch. The planet doesn't preserve skylines, but it sometimes preserves the fingerprints of how a world was organized. Now, imagine a scenario that isn't ours. Imagine a species that built most of its infrastructure underground, using tunnels and chambers for stability and temperature control. Underground structures can last longer than surface ones, but over millions of years they still face collapse, infill, and chemical alteration. Even so, a large network of tunnels could change groundwater flow, which could leave mineral deposits in unusual patterns. It could create zones of collapsed breccia, regions of disturbed strata that don't match typical karst processes. Again, it wouldn't be, here is a subway map. It would be, this rock volume has a strange pattern of voids and infill that suggests extensive excavation. Or imagine infrastructure built along ancient coastlines that are now far inland or long submerged. The physical structures might be gone, but the coastal sediments might carry traces of disturbance, unusual particles, or chemical markers washed into shallow seas. A future investigator might find a narrow interval in a marine sedimentary sequence that shows unusual contaminants or unusual erosion input from land, then a return to baseline. It might look like a brief episode of intense change. Or imagine an infrastructure that was largely ocean-based, floating platforms, biologically grown reefs shaped into habitat, or other systems that leave little in the rock record. In that case, the best hope would again be indirect signals, unusual distributions of materials, ecological changes, chemical fingerprints in sediments. The ocean is a good place to store layered records in some settings, but it also recycles its floor, so the survival of those records depends on where they were deposited. Each scenario shifts the expectation away from monuments and toward patterns. That's what deep time does. It forces you to ask not, what did it look like, but what did it change? If you enjoy this kind of slow thinking and you want more of it, you can subscribe to Just About Earth. You don't need to do it right now, especially if you're getting comfortable. but it's there if you want it. Now, there's one more step to make before the next idea arrives, and it's an important one. Infrastructure in our world includes communication. It includes writing, recording, transmitting messages across distance and time. It's easy to assume that if an earlier intelligence existed, it would leave messages, and those messages would be the most obvious proof. A carved stone, a durable inscription, a record meant to outlast its makers. But that assumption is sneaky, because it takes a very human habit and treats it like a universal rule. It also assumes that messages survive better than everything else, when in deep time, messages may be among the most fragile things of all. Writing relies on surfaces. Surfaces weather. Storage relies on materials. Materials break down. Even if something is designed to last, it still has to survive the planet's long routine. So as you sit with the idea of cities without cities, and as the picture shifts from skylines to sediment layers, it becomes natural to wonder about the quietest kind of disappearance. Not just structures erased, but stories erased. Not just roads ground into dust, but memories that don't travel forward. And once you start thinking that way, the next question almost asks itself, if something lived here long before us and built systems that mattered, why would we expect to inherit any clear message from it at all? And what does the Earth do to information when the timescale stretches beyond anything a language can hold? It's very easy to assume that if an earlier world existed, if some kind of organised intelligence lived here long before modern humans, then it would leave a message. Not necessarily a dramatic one, not necessarily a stone tablet that says, "Hello, future," but at least something story-like. A symbol. A carved mark meant to last. A record tucked away in a cave. A durable artifact placed somewhere safe. Something that feels like communication across time. That assumption feels natural because humans do it constantly. We leave notes on kitchen counters. We engrave names into metal. We write dates on the backs of photographs. We bury time capsules in schools and parks. We store our lives in files and cloud backups and libraries and archives. Even if we're not thinking about the distant future, we behave as if memory will carry forward. We act like tomorrow is a reliable place that will receive today's message. But Earth is not a reliable mail carrier, especially over deep time. On the timescales we've been talking about, millions of years, the most likely outcome is not that the message remains unread. The most likely outcome is that the message never makes it out of the envelope. This is one of the quietest, strangest parts of the whole idea. Not the thought that something could have been here, but the thought that even if it had been here, it might leave no story behind. No tale that travels, no words, no names, no map. No, we were here. Just traces that look like chemistry and sediment and maybe a pattern of change in living things. If you're listening in a place where your eyes are starting to feel heavy, you can let that thought settle without trying to solve it. Most of the time, the mind wants a story because stories are how we understand. The planet doesn't promise stories. It promises processes. To see why messages don't travel well, it helps to get concrete. What is a message physically? It's information stored in a medium. The medium might be a sound wave, but sound dies quickly unless it's recorded. The medium might be ink on paper, but paper is fragile. The medium might be carved stone, but stone weathers. The medium might be digital storage, but digital storage depends on a chain of technologies and energy that does not run on its own. Even the most robust medium you can imagine has a vulnerability. It has to survive the world it sits in. Consider a simple written page. In a normal room, it can last a long time if it's protected. In the open air, it starts failing immediately. Moisture makes fibers swell and break. Microbes eat organic material. Sunlight degrades ink and paper. Fire can erase in minutes. Flooding can erase in hours. A page that feels permanent in a library becomes temporary outside. Now consider stone, because stone is the classic fantasy of permanence. Humans have carved stone for thousands of years, and some inscriptions still exist. It's tempting to take that and extend it forward. If stone carvings can survive thousands of years, then maybe they can survive millions. But thousands and millions are not just different by a factor of time, they're different by a factor of what happens during that time. Over thousands of years, a sheltered carving might survive because it is not exposed to aggressive erosion, because the climate is relatively stable, and because nothing major happens to the site. Over millions of years, the odds of stable shelter drop. A cave can collapse or fill with sediment. A rock face can spool and crack and shed its surface layer. A region can be uplifted, eroded, buried, submerged, or heated. In many places, the very rock that holds the carving will not remain at the surface. It may end up under hundreds of meters of sediment, or be transformed under pressure into a different kind of rock, where the original carved surface no longer exists as a surface. Even if a carving survives as a form, it faces another problem: context. A message is not only marks, it's marks that are understood. An inscription is only a message if someone can interpret the marks as language. If they can't, it's just pattern. And pattern without interpretation is a silent object. We have a very good example of this from our own world that doesn't require any guesswork. There are scripts humans wrote not that long ago, relatively speaking, that were unreadable for centuries or longer. People could see the symbols clearly, but the symbols didn't transmit the meaning on their own. They needed a key, and the key was often another text or a bilingual inscription or a living tradition. Without that, you can have a perfectly preserved message that is still effectively gone. Even when we can decode a script, meaning can remain uncertain. We can translate words but miss references, jokes, cultural assumptions, and the emotional texture of what was said. And that's within human history, with humans as the intended audience, and with at least some shared cognitive and social framework. Now imagine a message from a non-human intelligence, or even from a human-like intelligence so far back that languages have not only changed, but the very concept of writing might not match ours. The odds that we would recognise it as a message, and not as natural markings, would be lower than most people feel comfortable admitting. There's also a timescale problem that is easy to overlook. A message designed to last must outlast not only the maker, but the entire chain of maintenance. Humans can keep a building standing for centuries if they repair it. Without maintenance, it falls apart quickly. The same is true for information systems. A library lasts because people protect it from water, insects, fire, and neglect. A digital archive lasts because someone keeps migrating formats, maintaining servers, replacing failing hardware, and powering the whole system. If you remove the human caretakers, the archive becomes a countdown. You can test this with a simple thought. Think about a piece of technology you owned 10 years ago. A phone, a laptop, a music player. Is it still usable today? Can you still charge it? Do you still have the cables? Do you still have compatible software to open its files? Now stretch that time scale. 100 years, 1,000, 10,000. It becomes clear very quickly that technology is not just objects, it's ecosystems of support. Without the ecosystem, the object becomes inert. So if an ancient world left digital messages, the physical medium might fail, and even if it didn't, the decoding chain would almost certainly break. A storage device without a compatible reader is like a locked box without a key. It might contain a story, but it doesn't deliver it. But what if they carve something into something extremely durable? Is a natural follow-up, and it's worth answering without dismissing it. Yes, some materials are durable. Certain ceramics can last long. Certain stones resist weathering. Certain crystals can be stable. In principle, you can imagine a message encoded in a very robust way. The problem is that durability is not the only requirement. Location matters. A durable object placed in the wrong environment can be destroyed by mechanical forces. A durable object placed on a coastline might be battered by waves, buried, and then subducted. A durable object placed on a floodplain might be carried away, broken, and dispersed. A durable object placed on a mountain might be worn down by frost and gravity. Even an object placed deep underground might be affected by groundwater chemistry, or tectonic stress. Over millions of years, the Earth does not offer many truly stable places, and even if you found a stable place, you run into a subtle irony. The most stable places are often geologically old and quiet, but they might not be the places where a civilization would choose to store messages, especially if that civilization lives near coasts and rivers and fertile land. People store what they value near where they live. They don't normally travel to remote cratons and bury artifacts for strangers who may never exist. A species could, of course, but it requires a particular motivation, the desire to communicate with a future that is far beyond anything they can personally verify. Humans flirt with that desire, but even we rarely act on it in a serious deep time way. Most of our messages to the future are symbolic. They're meant for a century or two, or for the idea of the future, not for a million-year recipient. Our time capsules are often sealed in places that feel permanent locally, like a cornerstone of a building, but those places are not permanent geologically. Our monuments are built in prominent locations, which are often prominent because they are exposed, and exposure is precisely what makes erosion efficient. So when people assume that an earlier world would leave a story, they are importing a very modern habit. The belief that storage and communication are easy. They aren't easy. They are labour. They are maintenance. They are a constant fight against entropy, which is just a calm way of saying that things tend to fall apart unless energy is spent to hold them together. This is where the concept of message begins to split in two directions. One direction is the message as narrative, words, symbols, diagrams, records. The other direction is the message as signal, a persistent change in the world that carries information about what happened. Narrative messages are fragile. Signals can be robust. Earth itself is a signal keeper. If something changes the chemistry of the ocean, that change can be recorded in sediments. If something changes the atmosphere, that change can show up in isotopes. If something causes a widespread extinction, that change can be visible in the fossil record. Those are messages of a kind, but they are not stories. They don't have names. They don't tell you what the builders thought of themselves. They don't tell you why they did what they did. They tell you that something happened, and they allow you to infer mechanisms. It's not a satisfying kind of communication if what you want is a conversation across time. It's satisfying if what you want is evidence. Now add another complication. Even if you had a narrative message that survived physically, it might not survive semantically. Semantics is the part of language that connects words to meaning. That connection is not fixed. It is maintained by communities. It changes over time. Words shift. Grammar shifts. References become obscure. Even within a few centuries, meanings can drift enough to confuse. Think about how quickly slang becomes incomprehensible. Think about how quickly technical jargon changes. Think about how often people misread old texts, not because the words are unclear, but because the cultural context is missing. Multiply that by thousands, and then by millions, and you begin to see the core issue. Language is not a static code. It is a living system that depends on continuous use. This means that for a message to travel in the narrative sense, it would need either an unbroken chain of learners or an encoding system that can be decoded without cultural context. Humans have tried to imagine such systems, and the exercise is harder than it sounds. Even a simple pictogram can be misread. A symbol that seems obvious can be interpreted differently depending on assumptions. A circle can mean a sun, an eye, a coin, a zero, a hole. Without shared conventions, a symbol is just a shape. If you're listening and you feel your mind starting to drift into the kind of puzzle that keeps people awake, you can set it down. The point is not to solve the perfect universal language. The point is to understand why deep time is hostile to meaning transmission. There's also the issue of scale and distribution. A message stored in one place is vulnerable. It can be destroyed by a local event. It can be buried in a location no one ever samples. It can be carried away. If you wanted to maximize the chances of being discovered, you might spread many copies across many environments. But spreading copies increases contact with environments that will destroy them. It also requires resources and planning. Again, it's a maintenance problem. In practice, most human information is concentrated in dense hubs, cities, libraries, data centres. Those hubs are exactly the places most vulnerable to future erasure. Coastal cities flood, river cities shift, political centres burn. Data centres require power. So even in our own case, if humans vanish suddenly, much of our recorded story would decay rapidly compared to the geological timescales we've been discussing. A few things might survive longer, some inscriptions, some durable objects, some deep-buried deposits, but the continuity of meaning would likely break quickly. If you want a slightly gentler way to hold this, you can think about the difference between evidence that something happened and a story about what it felt like. Earth is better at preserving the first than the second. A layer of sediment can tell you that a forest burned. It can preserve charcoal. It can show a sudden drop in pollen from certain plants. It can show a rise in erosion afterward. But it will not tell you what people said as they watched the smoke. It will not preserve the fear, the decisions, the arguments, the grief. That's not because Earth is cruel. It's because emotions and spoken words aren't durable materials. They exist in bodies and in communities, and when the bodies and communities are gone, the words go too. So if an ancient world existed and it vanished, it might vanish not only physically but culturally. Its songs and languages would disappear first, long before its structures. Its stories would be the easiest thing to erase because stories are not stored in rocks. They're stored in minds and in fragile media. This is also a good place to notice something about our expectations. We often imagine that a successful civilization must want to be remembered. That's another human projection. A species might be focused on survival and daily life, with no interest in leaving messages to unknown beings. It might not even conceptualize the future the way we do. It might not imagine itself as part of a grand timeline. It might not care about legacy. Even among humans, the obsession with legacy is uneven. Many people live without thinking about being remembered by strangers. They care about their immediate community. They care about their children. They care about the next season. The idea of leaving a message for someone millions of years away is not a universal instinct. It's a rare one. So a prior intelligence could have been busy, complex, and capable, and still leave no intentional communication. Not because it was primitive, but because it had no reason to write to us. Now, there's another kind of reason messages don't travel, and it's less philosophical and more mechanical. The Earth's surface is constantly being reworked, and that reworking doesn't respect storage. The places that feel safe to a living species are often the places most active geologically. Coasts are dynamic, river valleys are dynamic. Volcanic regions can be fertile and attractive, but volatile. The most stable regions can be harsh and resource poor. So a species that develops in rich, dynamic environments is also developing in environments that excel at erasing. If you take that seriously, it changes how you interpret silence in the geological record. Silence might not mean nothing happened. Silence might mean the message was never written, or that it was written in a medium that didn't survive, or that it was written in a place that got recycled, or that it survived but became unreadable, or that it is still there but no one has sampled the right spot. This is not an argument for believing in a prior civilization. It's an argument for being careful about what kind of evidence you expect, and what kind of absence you consider meaningful. There's a quiet, almost practical comfort in that, because it brings the question back to methods. If stories don't travel, then we shouldn't expect stories. We should expect patterns. We should expect signals that look like geochemistry and stratigraphy and fossil assemblages. We should expect to reconstruct rather than to read. And that reconstruction, if it's possible at all, would look less like translating a text and more like diagnosing an event from its long-term effects. If you like this slow kind of thinking, you can subscribe to Just About Earth. It helps the channel continue making episodes that treat big ideas gently, without turning them into a loud argument. You don't have to do it right now, especially if you're already settled and comfortable, but it's there if you want to come back. Now there's one more angle that matters here, and it's the angle that makes the next step of our exploration feel almost inevitable. When you realise that messages don't travel well, you start to see why a scientist would approach this whole topic as a question about signatures, not stories. A scientist doesn't need an inscription that says, "We had an industrial age." A scientist needs a set of markers that, taken together, are hard to explain by known natural causes. And once you start thinking in terms of markers, you stumble into an idea that has been discussed in a careful, speculative way by scientists before. The thought experiment about how you would detect a prior industrial civilization in the geological record, even if it left no readable message, even if it left no recognizable ruins, and even if all you had were thin layers, chemical ratios, and the planet's long edited memory to work with. There's a very particular moment in science where an idea stops being a campfire story and becomes a legitimate question. Not because anyone has found a secret artifact, not because a mysterious photo appeared on the internet, but because someone sits down and says, if this were true, what would we actually expect to see? And do we have the tools to look for that? That moment is the heart of what people sometimes call the Silurian question. It's not a claim that there was definitely a prior industrial civilization on Earth. It's a thought experiment written up by scientists about whether an industrial civilization that existed many millions of years before us would leave a detectable signature in the geological record. The name is playful, borrowed from science fiction, but the approach is very sober. Define what detectable means. Define what industrial would change, and then compare those expected changes to the kinds of changes we already see in Earth's deep past. If you let that land for a second, you can feel why this is such a useful pivot point in our larger conversation. Up until now, we've been circling around erasure, survival, faint clues, and the fact that stories don't travel well through deep time. The Silurian question takes all of that and turns it into something you can test, at least in principle. It asks, in a very practical tone, assume there was an earlier industrial age, how would we know? Oh, and if we couldn't know, what does that say about how we interpret the planet's record? A calm way to begin is to be clear about what industrial means in this context. It doesn't mean skyscrapers, it doesn't mean a familiar culture, it doesn't mean humans, and it doesn't even mean that the society had the same technologies we do. It means a civilization that uses energy at a large scale and transforms materials in ways that create a distinct, global-ish footprint. Something that moves from being a local ecological actor to being a planetary force, even briefly. The authors who frame this question, climate scientist Gavin Schmidt and astrophysicist Adam Frank, start from a simple observation. Our own civilization is already creating a recognizable set of markers, and if you want to imagine detecting a prior industrial civilization, the most honest starting point is to ask what our own footprint will look like after it's been buried, altered, and partially erased. In other words, the thought experiment begins with us. What will future geologists see when they drill into sediments that pass through our era? That is both humbling and slightly funny, in a dry way, because it means the first step in searching for ancient industry is to imagine ourselves as a strange layer in a rock core, not as a proud story, not as a glowing legend, but as an interval with odd chemistry, unusual particles, and a sharp change in biological signals. It's a bit like realizing that if your whole life was summarized as a single line on a graph, the line would not mention your favorite songs, it would just show a spike. Now here's where the Silurian question gets genuinely interesting. When Schmidt and Frank list the likely long-term markers of our current era, many of them look, at first glance, like things Earth has produced naturally before. Carbon isotope shifts, rapid warming events, ocean acidification signals, changes in sedimentation, spikes in certain metals, changes in ecosystems, and a wave of extinctions or rapid species turnover. These are not unique to humans. The planet has seen abrupt climate events and chemical shifts in the past, caused by volcanism, changes in ocean circulation, methane releases, and impacts. So even if our fingerprint is clear, it might not be obviously different from some previous episodes in the geological record. That's a key point of the Silurian question. The tricky part is not only preservation, it's distinguishability. If you're listening and thinking, so even if there was an earlier industrial age, it could blend in, that's exactly the uncomfortable possibility being explored. Geological records are not neatly labelled. A spike in temperature and a shift in carbon can be a volcanic episode, or it can be a massive carbon release from sediments, or it can be something else. If you want to say industry, you need markers that are difficult to generate naturally, or at least a combination of markers that together point strongly in that direction. This is where the discussion becomes a bit like detective work, except the detective is also studying how crime scenes decay over millions of years. If you only have one clue, you can easily be fooled. If you have several clues that all align in time and space, the story becomes harder to dismiss. One of the first practical questions in the Silurian thought experiment is whether an earlier civilization would have had access to the kind of energy sources that drive industrialization. In our case, a big part of the industrial footprint comes from burning fossil carbon. The authors point out that there has been fossil carbon available since at least the Carboniferous period, when large amounts of plant matter were buried and later became coal and other fossil fuels. So in principle, there has been fuel available for a long time in Earth history, long before humans existed. That doesn't mean anyone used it. It just means the energetic pathway was physically possible. Once you allow that in principle, the next step is to ask, if an earlier civilization burned large amounts of fossil carbon, what would it do to the geologic record? The most immediate answer is a carbon isotope signature. Fossil fuels are depleted in carbon-13 compared to many other carbon reservoirs, so massive fossil carbon combustion can shift the ratio of carbon isotopes in the atmosphere and oceans. That shift can be preserved in carbonates and organic matter laid down in sediments, giving future scientists a chemical tell that something rapidly perturbed the carbon cycle. But then comes the sobering part. Earth has already experienced carbon isotope excursions and rapid warming events without industry. One of the examples often discussed in this context is the Paleocene-Eocene thermal maximum, a rapid warming event about 56 million years ago that left a strong carbon isotope signal and major ecological impacts. The cause is still debated in details, but it is widely treated as a natural event involving a large carbon release. The Silurian thought experiment notes that if you saw a PETM-like event in the record, you might wonder what caused it, and you would have to be careful not to jump straight to industrial when there are plausible natural mechanisms. So carbon alone is not enough. Temperature change alone is not enough. Even a mass extinction is not enough because mass extinctions have happened for natural reasons. This leads to the next category: materials and chemicals that are rare in nature or arranged in odd ways. Modern industry produces synthetic organic compounds and unusual combinations of chemicals. Some of these might be persistent enough to leave long-term traces. The thought experiment discusses things like persistent pollutants, plastic residues, and heavy metal anomalies as part of an Anthropocene fingerprint. Heavy metals, for example, can accumulate in sediments near industrial activity, and if a civilization was extensive enough, it could create a measurable change in background levels across regions. Again, the planet complicates things. Metals can be concentrated by natural processes, and some pollutant-like signals can arise from volcanism or changes in ocean chemistry. So the question becomes more refined. Is there a particular pattern of element ratios, dispersal, and timing that would be more consistent with widespread industrial processing than with a single natural catastrophe? Schmidt and Frank's approach isn't to say here is the magic marker. It's to propose that you would need multiple lines of evidence, and they sketch tests that could plausibly separate a naturally driven event from an industrial one. That idea, tests rather than trophies, is what makes the Silurian question feel scientific. It's not about proving a favourite story. It's about defining what would count as a discriminating signal and then looking for it, while staying open to being wrong. Another set of markers they discuss involves nitrogen and phosphorus cycling, because industrial agriculture and fertiliser use can alter global biogeochemical cycles. In principle, large-scale fertiliser production and application could leave identifiable signals in sediments and isotope ratios. But here too, nature has its own ways of shifting nutrient cycles through climate change, ocean anoxia events, and biological evolution. What would matter is whether the changes are unusually abrupt, unusually widespread, and accompanied by other industrial-like signatures at the same time. There's also the question of radioactive signals, which people often jump to because it feels like a clear dividing line between nature and technology. Some radioactive isotopes can be produced by nuclear activity, and certain signatures could, in principle, stand out. Yet the real world is more complicated. Some isotopes have half-lives that make them poor long-term markers, and some can have natural sources. The thoughtful point here is not nuclear waste will prove everything, but radioisotopes might add to a broader fingerprint if the timing and context fit. If you're noticing a theme, it's this. The Silurian question is less about a single smoking gun and more about whether a civilization's footprint would be separable from the planet's own extremes. The authors emphasize that an industrial civilization's geological signature might resemble other known perturbations, which forces you to admit something quietly unsettling. Earth's natural history already includes events that, in some respects, look Anthropocene-like in their rapidity and magnitude. Our era might not be the first time the planet has seen abrupt global-scale change. It may be the first time the cause is a technological species, but the record of abrupt change itself is not unique. This doesn't make the idea of a prior industrial age likely. The authors are quite clear that they do not think it's probable that there was a prior industrial civilization before ours. The value is in sharpening how we think about detectability and in connecting Earth science to astrobiology. If we want to search for technological civilizations elsewhere, we need to know what kinds of planetary fingerprints technology leaves and how long those fingerprints last. In that sense, the Silurian question is partly about Earth and partly about methods for recognizing technology as a geological force on other worlds. And now we can address the name, because it's easy to misread it as implying the Silurian period on Earth specifically. The name is actually a nod to Doctor Who, where Silurians are a fictional species said to have lived before humans. The humour is intentional, and it's doing something useful. It lowers the emotional temperature. It's a way of saying, we know this sounds odd, so let's handle it carefully and methodically. If you're listening late, there's something soothing about that tone. It's not breathless. It's not declaring secrets. It's treating the question like a calibration exercise for science. What can our instruments really tell us? And what do we assume just because we've never had to think otherwise? Now, there's an important practical detail in this whole discussion that often gets skipped in casual retellings. Even if an industrial civilization left a detectable signal, the signal would only be detectable if it ended up in rock we still have access to. Earth's surface is not an even archive. Large portions of the ocean floor are geologically young because the crust is recycled. Many old sediments have been subducted, metamorphosed, or eroded away. So the detectability problem is not just did it leave a signal, but did the signal get stored in a surviving archive that we have sampled? This is where the thought experiment becomes almost uncomfortably relevant to our earlier theme about messages not travelling. The planet does not guarantee delivery. You can have an event, you can have a signal and still lose the record. The absence of a record is not proof of absence. It's a reminder that the filing cabinet has had pages torn out and thrown away. At this point, you might ask yourself a small, gentle question that keeps the mind from spinning. If you were a geologist in the far future and you found a strange boundary layer, what would you do? You would compare it to known events. You would look for multiple independent markers. You would ask whether the pattern repeats across different basins. You would test alternative explanations and see which one fits best. You would probably not leap straight to an ancient civilization did this, because that hypothesis would have a high burden of proof. You'd keep it as a low probability option, unless the data forced you to raise its probability. That's a comforting thought, because it means the discipline is built in. The Silurian question doesn't open the door to believing anything. It opens the door to asking better questions about what our planet can preserve and what kinds of planetary-scale fingerprints technology might leave. There's also a subtle humility in the conclusion that our own signature, while real, might not be as uniquely identifiable as we like to think. We tend to imagine ourselves as the planet's most distinctive event. From a deep time perspective, the planet has endured enormous disruptions before. Our era may look like another abrupt perturbation among several, unless the combination of markers, synthetic compounds, unusual element distributions, a particular pattern of isotopes, and the biological consequences adds up to something that really stands out. If you're still awake enough to smile at a small joke, here it is. Future scientists might not find our best novels, our music, or our carefully curated photos. They might find our carbon anomaly, our metal traces, and a thin layer of odd chemistry, and they'll call it an event. That's not an insult. It's just how long-term records work. The planet remembers in its own language. And if you like this calm way of talking about unsettling questions, you can subscribe to Just About Earth. It helps the channel reach the kind of listener who would rather think slowly than argue loudly. You don't need to do anything immediately. Just keep it in mind for whenever it feels convenient. Now, the most useful thing the Silurian question gives us is a map for what comes next in our exploration. It tells us that if a prior industrial age existed, it might not leave ruins, and it might not leave stories, but it could leave a fingerprint. That fingerprint would probably look like a combination of geochemical anomalies and ecological disruption, captured in sedimentary archives that survived long enough for us to sample. Which raises a very practical issue that we've been circling around without naming directly. If those archives are uneven and scattered, then a lot of our searching instincts might be pointed at the wrong places, and the evidence, if it exists at all, would tend to hide in the quiet parts of the planet's memory, in basins and layers that don't look dramatic from the surface, but keep time patiently in thin, readable sheets. There's a certain habit the human mind has when it hears the phrase hidden evidence, and it's almost automatic. It imagines something tucked behind a wall, or buried in a desert, or sealed in a cave with a dramatic entrance. It imagines a place you could point to on a map and say, "It's there." Maybe you picture someone brushing sand away from a stone doorway, or shining a flashlight into a chamber and finding something intact and waiting. That habit makes sense, because it matches how many discoveries happen within human history. If something is lost for a few centuries or a few thousand years, it can still be found in recognizable form, especially if it was built of stone, and it happened to end up in a place that didn't chew it up too fast. A shipwreck can sit on a seafloor for a long time, a city can be buried by ash and preserved, a cave can protect paintings. The world can keep surprises like that when the time window is small enough and the conditions are just right. But the moment you stretch the time window into millions of years, the mind's default picture becomes the wrong picture. Not wrong in a scolding way, just wrong in the same way it would be wrong to search for yesterday's weather forecast by digging up your backyard. The information you want might still exist, but it won't be stored where your instincts want to look. So when we ask where evidence of an earlier presence would actually hide, we have to change what we mean by evidence, and we have to change what we mean by hide. It's not hiding in the sense of being deliberately concealed. It's hiding in the sense of being stored in places that don't look like storage, and in forms that don't look like messages. If you're listening from somewhere comfortable, it can help to imagine this question as a practical problem rather than a mystery. Suppose you wanted to find out whether something unusual happened on Earth a very long time ago, something big enough to leave a planetary fingerprint. You would not start by hiking around and hoping to spot a ruin. You would start by thinking like the planet. Where does Earth keep long-term records? Which environments build layers steadily and protect them? Which places are quiet enough to preserve subtle signals without constantly stirring them up? A lot of people, without meaning to, search the wrong places because they search where the evidence would be obvious. They search on the surface. They search in dramatic landscapes. They search in places that feel ancient to human senses, like deserts with exposed rock, or mountain ranges with stark cliffs, or remote islands that look untouched. They search where a camera can travel easily, and where a story can be told in a single image, a strange rock formation, an unusual line on a hillside, a perfect shape seen from above. The problem is that dramatic landscapes are often dramatic because they are active. A cliff face is a cliff face because it is breaking and shedding rock. A mountain is a mountain because it is being uplifted and eroded at the same time. A desert with exposed bedrock is often exposed precisely because wind and occasional water have stripped away softer material, leaving a surface that is constantly being sandblasted. These places feel ancient to us because they look old and raw, but in terms of preserving delicate layered records, they can be terrible. Earth's best archives tend to be boring. They tend to be places where sediments settle gently and repeatedly, like pages stacking in a slow printer that never runs out of paper. They tend to be basins, low spots, quiet underwater regions, lake bottoms, shallow seas that became land, continental shelves where layers accumulate, and deep marine settings where tiny shells and dust rain down steadily. They tend to be places that, from the surface, can look like nothing special at all. That mismatch between what looks exciting and what keeps records is the first reason we end up searching the wrong places. There's a second reason, and it's even more basic. Coastlines move, rivers move, seas rise and fall, continents drift. The places where a civilization would most likely concentrate, if it behaved anything like ours, are often the places least likely to preserve simple, obvious artifacts over deep time. Coastal plains, river deltas and fertile lowlands are attractive because they offer resources and easy movement. They're also the places that get flooded, buried, reworked, and sometimes subducted. Over millions of years, a coastline can be nowhere near where you'd expect it to be. A city built near a shore can end up far inland as sea levels fall, or underwater as sea levels rise, or smashed and folded as plate boundaries shift, or erased as a river system rearranges the whole region. So if someone says, if there was an earlier civilization, where are the coastal ruins? The gentle answer is that coastlines are not reliable shelves. They are conveyor belts. They move sediment and they rewrite themselves. They don't just hide things, they grind them down and spread them out. Now, if we take the Silurian-style thought experiment seriously, the evidence we'd expect isn't a preserved skyline. It's a fingerprint, and fingerprints don't sit on mountaintops. They get recorded in layers. That means the question becomes, which layers survive, and where do they sit today? Here is where the geography of preservation becomes almost its own character. There are three big categories of archives that matter: marine sediments, continental sedimentary basins, and local traps that preserve unusually well. Marine sediments are tempting because they can record global signals. The ocean covers most of the planet. It receives the runoff from continents. It exchanges gases with the atmosphere. It stores carbon in sediments. It contains microscopic organisms whose shells and chemistry record temperature and acidity. If something perturbed the planet at large scale, the oceans would often show it. But marine archives come with a warning label: the seafloor is not forever. Oceanic crust is created and destroyed. Much of the deep ocean floor is geologically young compared to the age of the planet. That means a perfect archive can be erased simply because the page it's written on is eventually recycled. In practical terms, this suggests something important. The best marine records of very old events are not necessarily sitting on the modern deep ocean floor waiting to be drilled. They might instead be found in sedimentary rocks that formed in ancient seas and were later uplifted onto continents, preserved in mountain belts or stable regions as marine limestones, shales, and other sedimentary sequences. That's the first place evidence might hide in plain sight. Rocks on land that were once ocean sediments. You can walk on them, you can build houses on them, you can drive over them, and inside them, if you have the right tools and the patience to sample carefully, there can be chemical and biological records of ancient ocean conditions. Continental sedimentary basins are another key archive. These are regions where sediments pile up over a long time, often because the crust is subsiding. Think of them as slow sinks, where rivers, lakes, and shallow seas deposit material year after year, and the basin keeps accepting it. If you want long-lasting storage, these basins are the closest thing Earth offers to a filing cabinet, especially if they remain relatively stable and don't get heavily metamorphosed. What makes basins so important is that they can preserve long continuous sequences. You can find millions of years stacked in order, sometimes with enough resolution to see relatively brief events as distinct intervals. If an earlier industrial-like event happened, and if it left a chemical anomaly or changed sedimentation, a basin might preserve that as a thin but readable signature. The catch is that basins are not always dramatic. Many are covered by younger sediments or vegetation. Many are under farmland. Many are under cities. Some are offshore. You don't see the archive with your eyes. You access it by drilling, coring, sampling outcrops, and building maps of strata. In other words, the evidence hides below the surface, not because it's secret, but because that's where sedimentary memory lives. Then there are local traps. These include things like certain lake beds, anoxic environments where oxygen is low and decay slows, rapidly buried deposits, and unusual settings that can preserve fine detail. A deep lake with layered sediments can hold a detailed record of environmental change for tens of thousands or hundreds of thousands of years, and in some cases longer if the geology allows it. An anoxic basin in a sea can preserve organic rich shales that capture chemical signals. A rapid burial under ash can preserve a snapshot. These are not necessarily where you'd find ruins, but they are where you might find sharp transitions and concentrated signals. So far, this might sound like the answer is simply, look in sedimentary layers. That's true, but it's not the whole picture, because even within sedimentary layers you can search the wrong way. One mistake is looking for the wrong scale. People sometimes imagine that the evidence would be a single object, a single anomaly, one dramatic sample. But deep time signals are often statistical. They show up as patterns across many samples and many sites. One core might miss it. One outcrop might not include the interval you need. One basin might have an unconformity, a gap where erosion removed the very layer you'd want to inspect. Another basin might preserve it beautifully. If you treat the problem like a scavenger hunt for one artifact, you'll almost always come up empty and conclude nothing is there. If you treat it like a pattern recognition problem across multiple records, you have a chance of finding something meaningful if it exists. Another mistake is trusting surface exposures too much. Surface outcrops are valuable, but they come with biases. The very reason an outcrop is exposed is often that erosion is active there, which can remove delicate layers and distort structures. Surface rocks can be weathered, leached, and chemically altered. A subtle chemical signal in a layer can be blurred by groundwater moving through cracks over long time. So if you're searching for small anomalies, you often want fresh samples from drill cores that have been protected from surface alteration, or at least you want to account for weathering effects. A third mistake is assuming the evidence would be located where a civilization lived, rather than where its byproducts ended up. This is a quiet but crucial shift. If you want to find evidence of large-scale activity, you may have more success looking downstream than looking at the supposed city site. Rivers carry runoff, winds carry dust, oceans receive sediments. The byproducts of land activity often end up deposited in aquatic basins. In deep time, those basins can become the best record. In other words, the signature might hide in offshore mud layers, not in the eroded remains of a settlement. This is already how some kinds of modern environmental reconstruction works. If you want to know when a region experienced heavy metal pollution, you can examine lake sediment cores where particles settled and accumulated. If you want to see shifts in vegetation, you look at pollen preserved in sediments. If you want to track changes in erosion, you examine grain size and deposition rates. The same logic extends backward in time. The archive is often not the activity site, it's the receiving basin. Now let's talk about why we gravitate toward the wrong places anyway, because understanding that impulse helps you avoid it. We are visual creatures. We like evidence we can see. We like shapes. We like objects. We like before and after photographs. A chemical isotope ratio doesn't feel like a story. A thin layer of unusual carbon doesn't feel like a discovery you can hold. A graph doesn't feel like a ruined temple. So the mind resists the idea that the best evidence might be a set of measurements rather than a dramatic object. There's also the issue of accessibility. You can hike to a desert line and take a photo. You can point to a rock formation and speculate, but drilling cores, mapping basins, and running geochemical analyses is expensive, slow, and collaborative. It doesn't fit the one explorer finds the secret storyline. It fits the many people take careful measurements and argue politely over interpretation storyline. The second one is closer to reality, but it's harder to sell as adventure. Still, for our purposes, the calm approach is to accept that the real work happens in unglamorous places, in cores stored in warehouses, in thin sections under microscopes, in isotope labs, in stratigraphic charts that look like complicated barcodes. That's where the planet's long memory is decoded. This is also why the question, where would evidence hide, is slightly misleading. Evidence doesn't just sit somewhere waiting. It has to be sampled. The planet is big, and our sampling is sparse. We have drilled many cores and studied many outcrops, but in the context of Earth's surface area and history, it's still a thin set of pinpricks. Many regions have never been cored deeply. Many sequences are poorly dated, many basins are understudied, so even if there were a subtle anomaly in the record, it might simply be outside the regions that have been measured in enough detail. That's not an excuse to believe anything, it's just a description of how incomplete sampling can be. Now, to make this more concrete, imagine you were trying to detect a brief industrial-like episode that lasted, say, 10,000 years. 10,000 years is a long time to us, but in the sedimentary record of millions of years, it can become a very thin layer, sometimes millimeters in some environments. If that layer exists, it might be easy to miss unless you know exactly where to look and you sample at the right resolution. It might be present in one basin and absent in another. It might be blurred by later mixing. It might be cut out by erosion. So the evidence could be there, but in a practical sense, it could be hard to capture. That leads to another point about searching the wrong places. Sometimes we search with the wrong resolution. We look at the record in broad strokes and miss thin signals, or we look at individual sites and miss global patterns. The problem demands both, fine resolution where it matters, and broad comparison across multiple sites. If you're listening and you notice your mind getting a little busy with all these constraints, you can let it relax. The message is simple. The planet keeps records, but not in the places and forms we instinctively want. Now, let's address a common mental picture that tends to pull attention off track. The idea that if something existed before us, it would be buried deep in a straightforward way, like a time capsule. The truth is messier. Burial is not always vertical. Sediments can be folded, faulted, tilted, and duplicated. Layers can be repeated in thrust belts. Older rocks can be pushed over younger rocks. Pieces can be transported. Unconformities can remove large spans of time. So deep does not always mean old, and shallow does not always mean young. If you're searching for an ancient signal, you need stratigraphic context, not just depth. That's another reason surface treasure hunting fails. It treats geology like a stack of pancakes where older always means deeper and everything stays in order. Earth's crust is more like a stack of pancakes that has been bumped, folded, partly eaten, and then restacked. So where would evidence actually hide? It would hide in places where the pancakes stayed relatively orderly. Stable basins, long-lived sedimentary sequences, and records that have been dated and correlated across regions. It would also hide in microfossils and mineral grains, because those are tiny recorders of chemistry. Microscopic organisms that build shells like foraminifera can record ocean temperature and chemistry. Their shells accumulate in sediments. The ratio of certain isotopes in those shells can tell you about climate shifts. If an industrial-like event altered atmospheric composition and warmed the planet, it could show up indirectly in the microfossil record. Not as a story, but as a measurable change. It would hide in organic-rich shales, because organic matter can preserve chemical signatures of carbon cycling. If a sudden change occurred, the isotopic composition of organic matter might shift. That's the kind of clue that would be invisible to a casual observer and obvious to a lab. It would hide in ash layers and dust layers, not because ash is industrial, but because ash layers can serve as time markers. If you can correlate layers across regions using volcanic ash horizons, you can line up records from different basins and see whether anomalies occur at the same time. This is how you turn scattered evidence into a coherent picture. It would hide in places that are already studied for other reasons. That's a subtle point with real importance. Scientists drill cores to study climate history, ocean circulation, mass extinctions, and Earth system changes. If a prior industrial-like event left a detectable signature, it might be discovered not because someone went looking specifically for ancient civilization, but because someone noticed an anomaly while studying a climate event, then asked a new question. Many discoveries happen that way, not by hunting the answer directly, but by bumping into it while doing careful work on something else. There's a gentle kind of realism in that. The planet doesn't hand you a clear label. You often have to notice that something doesn't quite fit, then test whether it's an artifact of your method or a real signal. Now, because this is just about Earth, it's worth bringing the whole idea back to your immediate world for a moment, because it keeps the topic from floating away. Take a second and think about where you are listening from right now. Are you in a place that feels stable? A room that looks like it will be the same tomorrow? Most likely yes. That's how human life works. We build stable spaces and we trust them. Then consider the ground under you as a kind of archive. The floor might be concrete. Under that might be fill. Under that might be soil. Under that might be older soil. Under that might be sediment deposited by a river that once flowed differently. Under that might be rock formed in an ancient sea. None of that is visible, but it's there. The evidence of countless earlier worlds is under your feet, even if your day-to-day life doesn't require you to think about it. That is the true hiding place. Not a secret vault, but the ordinary layered structure of the planet. If you enjoy this calm way of exploring big questions, you can subscribe to Just About Earth. It's the quiet kind of support that keeps these episodes coming, and you can do it whenever it feels convenient. Now, one more practical problem remains, and it's the reason the search can feel like it's aimed at the wrong places even when you're looking at the right rocks. Even if the evidence is stored in basins and cores and layers, you still need a way to interpret it. You need a way to translate layers into behaviour and anomalies into causes without fooling yourself. That requires a kind of work that looks a little like archaeology, but isn't limited to human artefacts. It's a method of reading the planet as memory, using chemistry, sedimentology, fossils and careful correlation, almost the way you'd read a long medical record to understand what a body went through. And that's where we naturally arrive next. Because once you accept that the best evidence would hide in quiet layers rather than dramatic ruins, the question becomes how you would actually do the reading, what tools you'd use, what kinds of signatures you'd trust, and how you'd build a picture of an ancient presence if it existed at all, from the faint, stubborn traces the Earth is capable of keeping. If you've ever watched someone do careful restoration work on an old painting, you've seen a certain kind of patience. They don't scrape at the surface and hope for the best. They look for layers, they test small areas, they use tools that can tell the difference between original pigment and later varnish, and they accept that the goal isn't to force the painting to say what they want it to say. The goal is to let what's there become readable again, without damaging it in the process. A new kind of archaeology, the kind we're talking about tonight, feels closer to that than to the classic image of someone brushing sand off a statue. It's not focused on finding one dramatic object. It's focused on learning how to read a planet that has been recording, overwriting, and compressing its own history for billions of years. It treats Earth less like a museum and more like a memory system, with all the strengths and flaws that memory implies. Because memory is not a perfect archive. Human memory keeps certain details and loses others. It blends events together. It can preserve a strong emotional signal while dropping the exact date. It can keep the outline of something while changing the colour. Earth does something similar, except its memory is made of layers, minerals, fossils, isotopes, and the physical rearrangement of landscapes. So if you wanted to seriously explore whether we've missed signs of an earlier presence, you'd need methods that don't depend on obvious ruins. You'd need a way to take thin, scattered traces and build a coherent picture, while constantly checking yourself for the ways you might be fooling yourself. That's what this new archaeology is. Not a new set of fantasies, but a new set of reading skills. Before we go further, take a moment to notice where you are again. Has your posture changed since you started listening? Are your shoulders lower? Is your breathing slower? And what time is it where you are right now? It can be grounding to remember that while we talk about millions of years, your own moment is still here, and it still counts. When people hear archaeology, they usually think objects. But archaeology, at its core, is about behaviour inferred from traces. A potsherd is not important because it's a potsherd. It's important because it implies a set of actions: gathering clay, shaping it, heating it, storing food, organising daily life. A broken wall is not important because it's broken stone. It's important because it implies choices about where to build, what to defend, how to live together. When you expand archaeology into deep time, the word trace changes shape. The traces become less like pottery and more like patterns in rock. The behaviours become less like cooking and more like changing the chemistry of air and water, shifting erosion rates, moving materials in unusual ways, or creating a distinctive signature in sediments. The question becomes, can we infer purposeful activity from the planet's own records in the same way we infer ancient human behaviour from fragments? That sounds ambitious, but the comforting part is that Earth scientists already do something very similar, just with different causes. They read past climates from chemical ratios. They infer volcanic episodes from ash layers. They reconstruct ocean oxygen levels from the chemistry of sediments. They detect mass extinctions from sudden changes in fossils. They model how carbon moved through the atmosphere and ocean tens of millions of years ago. In a sense, Earth science has always been a kind of archaeology. It's the archaeology of processes. The new part is the willingness to include technology and intelligence as potential processes, not as a default explanation, but as a category of cause that can be described, tested, and ruled in or out. It's the same move the Silurian thought experiment makes. Define what you'd look for, then see whether any part of the record matches it, while keeping natural explanations front and centre. So what does reading the planet like a memory look like in practice? It starts with stratigraphy, which is the simple idea that layers matter. Sediments settle, accumulate, and turn into rock, and those layers preserve sequences. A river flood lays down a layer, a quiet season lays down another, a volcanic eruption lays down ash. Over time, these become stacked pages. Of course, the pages get torn and folded. There are gaps where erosion removed layers. There are places where the book was burned, metaphorically, by heat and pressure. But in many sedimentary basins, the sequence is readable enough to tell you what happened first, what came later, and whether something changed abruptly. That sequence is the foundation, because without ordering, you can't tell a story at all. A fossil out of context is a curiosity. A fossil within a dated layer is information. The next piece is dating, and it matters more than most casual conversations about deep time admit. When someone says millions of years, it can sound like a vague blur. In reality, The difference between 50 million and 55 million years is huge if you're trying to link an event to a particular climate shift or biological change. So this new archaeology depends on building timelines using multiple methods: radiometric dating of volcanic ash layers, magnetostratigraphy that uses changes in Earth's magnetic field recorded in rocks, biostratigraphy that uses the appearance and disappearance of certain fossils and correlations across different basins. These are not glamorous methods, but they are what keeps you honest. They let you say, this layer here lines up with that layer there, which is how you stop seeing isolated oddities and start seeing patterns. Once you have layers in order and roughly dated, you can start reading signals. Geochemistry is one of the most powerful parts of this, because chemistry can survive when objects do not. Isotopes, in particular, are like subtle fingerprints. Carbon isotopes can tell you about changes in the carbon cycle. Oxygen isotopes can reflect temperature and ice volume. Nitrogen and sulfur isotopes can reflect nutrient cycling and oxygen levels. Even trace elements can hint at conditions in oceans and on land. If a civilization-like process altered the atmosphere and oceans quickly, it might leave an isotopic shift that looks like a boundary, a sudden change that then slowly relaxes back. But the key is to read those shifts with humility, because nature produces shifts too. The way you get beyond "this looks weird" is to build a multi-proxy picture. That means you don't trust one signal alone. You look for a cluster of signals that agree. For example, if you see a carbon isotope excursion, you'd also look for evidence of warming in oxygen isotopes, changes in microfossil assemblages that suggest ocean acidification or shifting habitats, sediment changes that suggest altered runoff, and maybe changes in certain trace metals that respond to oxygen levels. If multiple lines point to a rapid, global disruption, you can be more confident that something large happened. You still may not know the cause, but you've narrowed the possibilities. This is where the memory metaphor becomes especially useful. When you remember a day that mattered, you don't recall it through one detail alone. You recall the weather, the place, what you were wearing, what you heard someone say, how your stomach felt, what happened right before, what happened right after. Those different details reinforce each other. Earth works similarly. A single measurement can mislead. A web of measurements can stabilize the picture. Another tool of this new archaeology is sedimentology, the study of how sediments are deposited and what that says about the environment. Grain size, layering style, mineral content and sedimentation rate are not just rock facts. They tell you about rivers and storms and sea levels and erosion. If a landscape suddenly starts shedding more sediment, that is recorded. If forests disappear and soils erode rapidly, rivers deliver different loads. If coastlines migrate, the kinds of sediments change. These are physical signatures that can be matched with chemical and biological ones. So, if you imagine a technologically active species that cleared large areas, mined resources, or built extensive networks, the direct structures might vanish, but the indirect physical signature could remain. A period of elevated erosion, changes in sediment supply, altered river behaviour, and unusual deposits in receiving basins. That would not prove industry, but it would provide a context where an industrial hypothesis could be tested alongside natural ones. Then there's paleontology, which people often think of as bones, but for deep time reading, microscopic fossils can be even more important. Tiny organisms in the ocean, like foraminifera, coccolithophores, and other plankton, respond quickly to changes in temperature, acidity, and nutrients. Their shells accumulate in sediments in enormous numbers. That means the ocean floor, when preserved, can hold a high-resolution record of global environmental change. A rapid disruption leaves a trace not only in chemistry but in who lived and who didn't. This matters because intelligent activity at planetary scale, if it happened, would likely stress ecosystems. Maybe not immediately, maybe not in the same way ours does, but large perturbations tend to ripple through food webs and habitats. So, one line of inquiry in this new archaeology would be to look for unusual combinations. a sharp environmental signal paired with biological changes that look like rapid pressure rather than slow evolution. It's important to stay careful here, because life has been stressed many times without intelligence. Mass extinctions, ocean anoxia events, and abrupt warmings have happened naturally. The new archaeology doesn't treat every extinction as suspicious. It treats extinctions as part of the planet's baseline story and asks a more refined question. Are there events where the pattern of change looks strangely like what an industrial civilization might do? And if so, do we have any distinctive markers that could separate that from known natural drivers? That brings us to the more exotic tools, the ones that sound almost like science fiction, but are used routinely in earth science. Biomarkers, for example, are molecular fossils, complex organic molecules that can persist in sediments and tell you about past life and environments. Certain compounds indicate certain types of organisms. Others indicate oxygen levels or temperature conditions indirectly. If a large-scale disruption occurred, biomarkers might show shifts in ecosystems in ways that complement isotopes and fossils. Biomarkers can also, in principle, preserve traces of unusual organic chemistry, though the further you go in time, the more those molecules are altered and the more you have to interpret them carefully. There's also the study of unusual minerals and synthetic-like materials. Humans create materials that are rare in nature, or that occur in unusual combinations. Over long time, those materials can break down, but some mineralogical fingerprints could remain. Even the distribution of certain elements in unusual ratios could be a hint. The new archaeology would treat such hints as tentative, and would look for them across multiple sites because one strange sample is more likely to be contamination or a local oddity than a global signature. Remote sensing plays a role too, not in the satellite finds lost city from orbit sense, but in the mapping sense. High-resolution topography, gravity measurements, magnetic surveys, and seismic imaging let scientists see structures underground. Basins, faults, buried river channels, and the shapes of sedimentary packages. This is how you find the places where the archive might be thick and continuous. It's how you avoid spending all your time staring at dramatic landscapes that are actively erasing themselves. You use the tools that show you where the quiet accumulation happened and where it survived. If you want a simple analogy, think of it like looking for a person's medical history. You wouldn't search their skin for the whole story. You'd look at their records, blood tests, imaging, patterns over time. You'd look for changes that are consistent across multiple measures. You'd pay attention to sudden shifts. You'd ask about confounders and alternative explanations. That's very close to what Earth scientists do when they reconstruct past events. The new archaeology is simply adding a new category of potential patient behaviour to consider, while keeping the standards of evidence strict. Another part of reading the planet like memory is modelling. Earth system models and climate models can simulate what happens when carbon is injected into the atmosphere, how oceans respond, how temperatures change, and what kinds of chemical signatures might be left behind. Models don't prove what happened, but they help you test whether a proposed cause could produce the observed pattern. If you see a particular isotope excursion and a particular warming signal, you can test different causes and see which ones produce similar signatures. If you ever want to keep your feet on the ground in a topic like this, modelling is one of the best anchors because it forces hypotheses to produce numbers, not just vibes. Of course, models have limitations. They depend on assumptions. They simplify complex systems. That's why they're paired with data. Data without models can be confusing. Models without data can drift. Together they form a loop. Observe, hypothesize, simulate, test, revise. If you're noticing that this new archaeology sounds like a lot of work, you're right. And that's part of why this topic hasn't turned into a mainstream field with clear answers. It's not easy. The planet is huge. Sampling is limited. Signals can be subtle. Natural explanations are strong. And the risk of self-deception is real. When you search for something unusual, you can become too eager to interpret ambiguity as confirmation. so the discipline matters. One of the strongest disciplines in this kind of work is to start with the assumption that natural processes did it, and then ask what data would force you to consider an alternative. That doesn't mean being closed to alternatives. It means being careful about the order in which you accept them. A related discipline is blind analysis, or at least a mindset like it. In some fields, researchers analyze data without knowing which sample is which until after methods are locked in, to reduce bias. Earth science can't always do that neatly, but the principle still applies. Define your criteria before you see the results you want. Decide what would count as a significant anomaly. Decide how you would rule out contamination. Decide what replication would look like, then follow through. Replication is another cornerstone. A new kind of archaeology can't be built on one thrilling core sample or one anomalous rock. It has to be built on repeatable patterns found in multiple archives. If a signal is real and global, it should appear in more than one basin, in more than one region, in more than one type of record. It might not appear everywhere because records are incomplete, but it should appear often enough that it can be separated from chance. There's also the issue of scale again, and it's worth holding because it prevents extremes. If an earlier civilization existed but was small and local, its signature might be undetectable in global records. The new archaeology would then be limited by reality. You can't read what isn't recorded. If an earlier industrial civilization existed on a scale large enough to alter global chemistry, the signature becomes more plausible to detect, but it still might resemble known natural events. The tension is the heart of the Silurian question, and the reason it remains a question rather than an answer. Now, let's bring this down from the level of methods into a calmer human-level picture, because it's easy for all of this to start feeling like a lecture. Imagine a scientist holding a long cylinder of sediment core, split open like a book. The core is banded, darker layers, lighter layers, fine grains, occasional shells, tiny specks. To an untrained eye it might look like nothing. To a trained eye it's a timeline. Each band is an environment. Each shift is a change. The scientist takes samples at intervals. Those samples go to a lab. Measurements come back, a graph forms, patterns appear. Then the scientist compares that core to another core from a different place, and another, and another. Slowly, a broader picture emerges. That picture is never perfect. There are gaps, there are uncertainties, there are arguments about interpretation, but it's real enough that we can reconstruct ice ages, ocean temperature swings, volcanic episodes, and mass extinctions. The same approach could, in principle, detect other kinds of disturbances if they existed and if they left a signature. So the new archaeology is not a separate magical field. It's an extension of what Earth science already does, with a slightly different question at the centre. It also has a quiet connection to astrobiology that's easy to miss if you only focus on Earth. If we want to search for technological life elsewhere, we can't expect to find their cities directly. We might detect atmospheric chemistry that looks out of equilibrium. We might detect industrial pollutants. We might see climate signatures. We might infer energy use from planetary signals. Learning what technology does to a planet and how long those effects last helps us design better searches beyond Earth. In that sense, reading Earth like a memory is practice for reading other worlds. If you've been listening for a while and you like this slower, careful tone, you can subscribe to Just About Earth. It helps these episodes reach people who prefer to be guided through an idea instead of pushed toward a conclusion. And if you're already comfortable and don't want to move a muscle right now, you can just let that suggestion drift by and return to it later. There's one more aspect of this planet as memory idea that matters, and it's the emotional one, but we can keep it practical. When you think of Earth as having memories, you might be tempted to imagine the planet as hiding secrets on purpose. It's better and calmer to imagine it as a system that stores what it can store. The planet doesn't care whether we understand. It keeps running. Its memory is a side effect of how matter accumulates and transforms. That's why the new archaeology has to be comfortable with partial answers. Sometimes the record can tell you that something changed quickly, but not exactly why. Sometimes it can tell you that oceans warmed, but not which mechanism drove the carbon release. Sometimes it can tell you that ecosystems reorganized, but not what the first trigger was. That kind of uncertainty is not failure. It's the honest shape of deep time knowledge. And if an earlier presence ever did exist, and if it left anything at all, the odds are that we wouldn't meet it through a story. We'd meet it through that kind of partial reconstruction. A thin interval where multiple signals line up in an unusual way. A pattern that doesn't fit comfortably in existing categories. A quiet suggestion that prompts more sampling, more measurements and tighter tests. That's an unsettling idea if you want a clean narrative, but it can also be strangely comforting. It means that our relationship to the deep past is not about grand revelations. It's about attention. It's about learning the planet's language well enough to notice when it's saying something unusual. So if you take anything from this stretch, let it be simple. The evidence, if it exists, would most likely be a pattern stored in layers. The tools to read those layers already exist, but they demand patience, humility, and multiple independent checks. This is not treasure hunting, it's slow listening. And that sets up the final, gentler turn in the conversation, because once you imagine this careful layered reading as the best path, you can't help but wonder what it would mean emotionally and practically if the planet really did contain signs of an earlier presence, even faint ones, not as a sensational revelation, but as a shift in how we place ourselves in Earth's long story, and how we think about permanence, fragility, and the possibility that our era is not the first time a world on this planet reached a point where it could leave a detectable mark and then fade back into the background. If you let the idea sit long enough, it starts to change shape. At first it feels like a mystery, like a locked door somewhere in the past. Then, after a while, it begins to feel more like a question about how we understand ourselves and how we place ourselves inside a timeline that is bigger than any story we're used to telling. So let's take this gently, without trying to force an answer that isn't there. Right now, in the real world, we do not have confirmed evidence that an earlier industrial civilization existed on Earth millions of years before humans. If we did, it would not be a quiet curiosity. It would be the kind of discovery that reshapes textbooks. What we do have is a set of reasons to be humble about what the planet preserves, a set of methods that can read subtle signals, and a thought experiment that asks what our own footprint would look like when it becomes rock. That's already enough to change the mood of the question. Because the most important shift isn't maybe there were ancient factories. The shift is realizing how fragile the idea of certainty can be when the record is incomplete and the timescale is vast. Once you accept that Earth is both a recorder and an editor, you stop expecting the past to present itself in neat, readable sentences. And when you stop expecting neat sentences, the silence starts to feel different. Silence, in this context, isn't the same as emptiness. It's more like the silence you get when you walk into a building after everyone has left, and the air still holds a faint sense that something happened there, but you can't reconstruct the entire day from the stillness. You can see a chair moved, a cup left behind, a window open. You can infer, you can guess, you can test a few simple things, but you can't demand a full narrative from a room that wasn't designed to be a storyteller. Earth is like that, except the room is a planet and the stillness lasts millions of years. If you're listening from somewhere quiet, this is a good moment to check in with your own immediate world. Where are you right now? Are you lying down, sitting up, leaning against something? Is there a light on? And what time is it where you are? You don't need to answer out loud. Just notice that your life exists at one tiny point on the planet's timeline, and yet it's still your whole universe in this moment. That contrast is part of what makes big questions feel both heavy and strangely soothing at the same time. Now, Suppose for a second that we eventually found something that genuinely looked like a prior presence, not a dramatic object, but a pattern. A consistent, repeatable signature in multiple sedimentary records that didn't fit comfortably into known natural explanations. A cluster of markers that made careful scientists pause and say, we should consider another category of cause. What would it mean? It would mean, first of all, that Earth is capable of producing complex planet-shaping intelligence more than once. It would mean our existence is not a one-off miracle that happened once and then never again. It would mean intelligence is a possible phase in Earth's long biological history. Not necessarily a guaranteed phase, but a phase that can appear, run its course, and vanish. That's a simple statement, but emotionally it can land in a surprising way. Some people hear it and feel smaller, like a spotlight has moved away from humans. Some people hear it and feel less alone, like the planet is not a stage built for a single performance. Some people feel uneasy because it makes the future feel less secure, as if our fate might already be written in a pattern of a rise and disappearance. The truth is that it doesn't write our fate at all. It would only show that disappearance is possible, which we already know, and that the planet keeps going either way. A second meaning would be about time. It would force us to accept that first is not a meaningful comfort. Humans often take comfort in being the start of something. The first artists, the first builders, the first to understand the stars. But Earth history is full of firsts that were later followed by new firsts. The first forests, the first animals with hard shells, the first creatures to walk on land, the first birds, the first mammals. Each one was a major shift, and none of them meant the story ended. If we weren't Earth's first story in the sense of intelligent, organised activity, it would place us in that same pattern. Not as the centre, but as a part. Not the finale, but one chapter in a very long book, and the book doesn't stop because the chapter ends. A third meaning would be about how we define progress. We tend to treat the arc of history as a climb toward better and more advanced. In a human context, that story can make sense. Medicine improves, knowledge accumulates, tools become more capable. But on a planetary timescale, progress doesn't look like a straight line. It looks like bursts, collapses, reinventions, extinctions, and recoveries. It looks like the way a forest regrows after a fire, not a return to the exact previous state, but a new arrangement of life using the same sunlight and soil. If an earlier presence existed and disappeared, it would be a reminder that progress in one domain does not guarantee stability. More capability can come with more dependence. More complexity can create more points of failure. More energy use can create larger consequences. Those are not moral statements. They're engineering statements. Humans already live with this. A person with a simple life can often survive with fewer resources. A person whose life depends on many tightly connected systems is more vulnerable to disruptions. A global civilization is like that on a larger scale. It's powerful, but it's also sensitive. That leads to a fourth meaning that is not about the past at all. It's about the present. Because even if no prior industrial civilization ever existed, the exercise of imagining one highlights how our own signature might look in deep time. It forces us to see ourselves the way the planet will see us later, as an event recorded in layers. That can feel cold, but it can also be clarifying. We spend a lot of time arguing about what our era will be remembered for. Will it be remembered for art, or science, or conflict, or kindness? From the planet's perspective, if you strip away the human details, the memory becomes something like this. A sharp change in carbon cycling, a rapid warming, widespread movement of materials, unusual chemistry in sediments, and a biological reshuffling that includes extinctions and invasive species spread. That picture is not flattering or unflattering. It's just what a stratigraphic record is capable of holding. And once you see that, it's hard not to ask the quiet follow-up. If we would hate to be reduced to a thin chemical line in rock, what would we rather be? Not in terms of legacy, because the planet doesn't care about our legacy, but in terms of consequences. What do we want the living world to experience during our time here? What kind of planet do we want to hand forward, not to distant geologists, but to the people and animals and ecosystems that exist in the very near future? The idea of a prior presence, even as a thought experiment, can sharpen that question, because it reminds you that civilizations can be temporary, but damage can be lasting for a long time in human terms. Earth will recover eventually in deep time, but eventually can mean millions of years. If you're a living thing right now, those millions of years are not comforting. What matters is the next century, the next millennium, the next few thousand years. So if the thought makes you feel small, you can also let it make you practical. Smallness on a planetary scale doesn't mean your actions are meaningless. It means the scale of responsibility is local to your time, and that's still real. A fifth meaning would be scientific, and this one is karma. If we were not the first story, it would validate a certain way of thinking that is useful regardless of whether it finds anything. The practice of looking for subtle signatures rather than obvious ruins. It would encourage the kind of careful reading that improves Earth science anyway. Even if no prior civilization is ever found, the act of asking, what would it look like, pushes us to refine our understanding of climate events, carbon excursions, extinction patterns, and how long certain pollutants or materials persist in sediments. That's not just an academic win. It affects how we understand present risks. Better understanding of past rapid warming events helps us model future warming. Better understanding of how carbon moves through Earth systems helps us interpret what's happening now. Better understanding of sedimentation and erosion helps us manage landscapes. So the thought experiment is not wasted. It's productive even if the answer is no evidence found. There's also a connection to the wider universe that is easy to appreciate without getting carried away. If we ever want to detect technological life beyond Earth, we will likely not detect its buildings. We will detect its planetary fingerprints, if anything. Learning how fingerprints last, how they blur, and how they can be confused with natural processes is practice for that. It's like learning to read weather patterns before trying to read weather patterns on another planet. So even if Earth's past turns out to contain no prior industrial age, the methods and thinking still matter. Now, there's another meaning that is more personal and less scientific, but it's also very grounded. If we are not the first story, then being human becomes slightly less about being the crown of nature, and slightly more about being a participant in a long experiment called life. That can be relieving. It takes some pressure off. You don't have to carry the weight of being the single point of purpose in the universe. You can be one expression of a planet that produces many expressions. At the same time, it also makes the human obsession with permanence look a little funny, in the kindest way. We build as if our buildings will last forever, and then we watch a single flood, a single earthquake, or a single fire change a landscape in a day. We plan like we control everything, and then we learn over and over that we don't. If Earth had an earlier presence that vanished, it would be an extreme version of that lesson. But we don't need an extreme version to learn it. We can learn it just by watching how quickly nature reclaims what we abandon. There's a small, gentle humour here if you want it. Humans write "do not disturb" signs and expect the universe to respect them. The universe does not read signs. The universe reads chemistry and physics. And yet, we do have influence. That's the paradox we live in. We are temporary, but we are powerful. If you hold that paradox calmly, it starts to change how the idea of first story feels. It becomes less about status and more about stewardship. Not stewardship in a grand heroic sense, but in the plain sense of being aware that our actions ripple out into systems we depend on. Now, let's be honest about the emotional lure of the thought that something came before us. Part of the lure is that it feels like a secret. Humans love secrets, especially the kind that make the world feel deeper than daily life suggests. If you're tired, A secret can feel like a warm spark that keeps the mind awake. Sometimes that's fun, but tonight we can treat the spark gently. You don't need the spark to be entertained. You can let the question be interesting without letting it become consuming, because there is a version of this topic that becomes anxious. It becomes, if others rose and fell, we will too. It becomes a countdown. It becomes a doom story. That version is not useful. History, even when it includes collapse, is not fate. Systems can adapt. Humans can make choices. We can reduce harm. We can design resilience. We can change our energy systems. We can preserve ecosystems. We can do better science. We can do better politics. None of that requires believing in a prior civilization. It requires paying attention to our own. So if the idea makes your stomach tighten, you can loosen your grip. The point of looking at deep time is not to scare yourself into helplessness. It's to enlarge perspective. And perspective, when handled carefully, tends to calm more than it panics. There's also a version of the topic that turns into fantasy, where every mystery becomes evidence of an earlier intelligence. That version is not useful either. It replaces the hard work of understanding Earth with a story that can't be tested. The real wonder is not in making everything mysterious. The real wonder is in learning how much can be known from a thin layer of rock, a ratio of isotopes, a pattern of fossil shells, a small shift in sediment grain size. That kind of wonder is quieter, but it holds up better. So what does it mean, practically, to live with this question open? It means you can be curious without being convinced. It means you can support careful science that improves our understanding of the planet. It means you can accept that the past is bigger than our narratives, and you can also accept that your life is still meaningful within the scale you inhabit. It also means you can stop using "we're the first" as a comfort, and start using "we're here now" as a grounding fact. If you find this kind of calm exploration soothing, you can like the video and subscribe to Just About Earth. It helps the channel keep making episodes that don't rush, that don't shout, and that don't pretend every question has a neat answer. If you're already settled and your hands are still, you don't have to do anything right now. You can just remember it for later. Now, as we ease toward the end of this stretch of listening, there's one last image that might help, and it's very simple. Picture a beach at low tide. The sand is smooth in some places and patterned in others. There are footprints, small ones and big ones, and there are marks made by birds and waves and bits of seaweed dragged by water. Some of the marks are crisp and some are already fading. In an hour, most of them will be gone. Not because the beach is trying to erase them, but because the beach is moving. Earth is like that on a much larger scale. Marks appear. They last for a while. Then they blur. Some are preserved under the right conditions, like a footprint that gets covered by a sudden layer of sediment and turned into stone. Most are washed away. If there was something before us, it doesn't need to be a grand secret. It could be something modest that left a faint mark. Or it could be nothing at all. The planet's long record allows for both possibilities, and our job, if we want to call it a job, is simply to keep learning how to read the record without forcing it to tell a story it doesn't contain. And as you sit with that, you can let your attention soften again. Notice the weight of your body where it rests. Notice the temperature of the air. Notice the small sounds around you. The planet keeps turning, and the evidence of countless earlier worlds sits quietly under our feet, whether or not it ever includes an earlier kind of builder. If you stay curious, there will always be another angle to explore, another layer to read, another piece of Earth's memory to translate into something we can understand without rushing it. And that slow, careful curiosity is a good place to leave your mind as you drift further into rest.